Alright, hi everyone, welcome to the stream. My name is Joel. I graduated from University Mathematics in May 2022 and I've been teaching math since then, and I've even taught some university level modules, so this is one of them. I've taught calculus in the previous semester, and what has always been bugging me was the fact that epsilon-delta proofs when it comes to limits have never really been the most convenient to prove. So the trick now is that I am going to solve 100 limits using the epsilon-delta definition, and I've been giving it some thought recently as to how to make it a little bit more user-friendly. So I'm going to show you guys that in this stream. I have 100 questions and they're all in the description box below, so feel free to join in if you wish. The first thing to consider is the vanilla definition of the epsilon-delta limit. So we write that the limit as x approaches c of f of x equals to the real number L precisely when, for any epsilon bigger than 0, we can find some delta bigger than 0 such that if we get the inputs being constrained, then the outputs would also be constrained. And more precisely, what that looks like is, if the inputs are constrained as follows, then the outputs would be constrained as follows. And we're going to use this definition, and I'm going to introduce a little trick on this definition to answer all of our different epsilon-delta limit questions. So the first question that we have in store for us today, the first question, and I will use a different color to indicate the questions, is to use the epsilon-delta limit to establish this result. And here is the general strategy. The general strategy is to fix epsilon bigger than 0. We will need to choose delta to be something which will meet our requirements later on. So what requirements does it have to meet? It has to meet the requirement that this thing, f of x minus L, is smaller than this quantity epsilon. So here is usually the strategy. I would go to the side. F of x will in this case be 2x plus 5. We'll minus the term we are interested in. We'll do some algebra and a bit of factorization. And what that tells us is that when 0 is less than the inputs being constrained, the outputs, and usually what I might even do is to just write this as modulus of f of x, will be equal to 2 modulus x minus 4. We can simplify this to get 2 mod x minus 4. And our goal is to try to constrain this item by epsilon. That's our objective. We need a delta such that that will work. So we will reverse engineer by saying that 2 modulus x minus 4 is less than epsilon. This gives us mod of x minus 4 less than epsilon over 2. And what that tells us is that we need mod of x minus 4 to be ideally less than epsilon over 2. Now how can we choose delta such that's the case? We'll simply choose delta to be equal to epsilon over 2, and we are good to go. As you can see, this is one of the most basic examples, and even then it took a little bit of mind bending already. Could we do this in a slightly more user-friendly way? After having some thoughts and considerations, I've sort of found a simple trick that can help to make this much simpler. So we're going to do a new example, but I'm going to show you guys this trick using this new example. Okay. So we need to calculate the limit as x approaches to 4 of 3x minus 5 being equal to 7. we could go in as per usual. However, the trick observes that x approaching to 4 is a lot like x minus 4 approaching to 0. And the idea here is, well, what if we could use a substitution so that we don't have to mentally carry the x minus 4 inside of our heads? So what if we let this be equal to t? In this case, then this is the same thing as saying the limit as t approaches 0, but instead of 3x minus 5, it's going to be every instance of x, since x minus 4 is t, every instance of x will be replaced by 4 plus t. So what if we did this? 3 times 4 plus t minus 5. And furthermore, if we think about it, if the limit approaches 7, then the limit of everything minus 7 ought to approach 0. So the idea is sort of to introduce all of these little zeros so that we don't have to worry so much about too much bookkeeping. We can focus on trying to bound the output. Now what that still means is we still need to go on our epsilon delta hunt. However, now we don't have to worry so much about trying to keep all the items in check. So what do I mean by that? We'll fix epsilon bigger than 0 and we'll choose delta such that now instead of considering the x's, we're now going to consider the t's. So when 0 less than mod of t less than delta, our objective is to hopefully obtain mod of, and I'm going to call this whole thing g of t. G of t will be smaller than epsilon. This is what we are hoping to achieve, and this is what we are working towards in order to achieve. And basically for the rest of this stream, I will be using this approach for basically every single limit property. And I'll elaborate along the way as we continue. It's going to be a long time here. I've got a nice mocha frap with me, so stick around and it's going to be fun. So let's do that. We still need to do a bit of algebra, so let's just do that on the side. G of t is now 3 times of all of that. And now we can do a bit of simplifications here. Oops. Well, this could be problematic. I was supposed to show that this method is superior, and I believe it still is. But let me just take a look at where I might have messed up my algebra. Oh, I think I found my error. The 3 only applies to the 4 plus t, right? So actually this is the wrong step over here. Okay, pardon me. There is not a bracket over here. It's actually the brackets this way. There we go. I think this will clean things up. Let's try that again. 12 plus 3t minus 15 minus 7. Okay. 12 plus 3t. Well, this is still not very convenient. Let's take a. I believe things. If we did things properly, tons of things would cancel out. So let's go with it and see what happens. X is that 4 plus t. Okay, t equals to this. 12 minus 5 is positive of 7. What on earth? Why did I put 15 here? There's no 15 here. This is just 5. I'm sorry there. There we go. So 12 minus 5, there we go. There will be 3t plus 7 minus 7. This will be simply 3t. Now, why is that so beautiful for us? It's because now we can write this as mod of gt which is the expression we're interested in, we want it to be smaller than epsilon. This is actually modulus of 3t, and we can pull the 3 out because of the modulus properties. And now it's really much more straightforward to see when this guy is less than epsilon. This guy is less than epsilon. Well, let's just solve it and see what we get. Is when mod of t is less than epsilon over 3. And what that means is that we need mod of t to be less than epsilon over 3. And what do we choose delta to be? Simply epsilon over 3. So by making this substitution and doing the algebra really carefully, we simplify the problem and can solve epsilon deltas way more quickly. So let's do the next question. We are gonna have a long time here. It's gonna be 5. I have no idea how much time we're gonna spend here. But it's all in the notes. You can check out the questions inside the description and knock yourselves out over there. Let me write this question in white. This is the limit as x approaches 5 of 4x minus 12 equals to 8. So once again, we're going to make the substitution x minus 5 approaches to 0. This will become t, so that x equals to 5 plus t. So we are equivalently solving for the limit t approaches 0. Replace the x's with t's. Bring the 8 over. And if you want a proof as to why these work, it's also in the notes in the description. Alternatively, if you want a video on explaining how this shortcut is legitimate, the proof of why it works, and all the other shortcuts in the rest of this stream, feel free to leave it in the comment section below. Alright, so with that in mind, we're going to call this whole expression g of t. And so we need to fix epsilon bigger than 0, choose delta this way. Then when 0 is less than mod of t less than delta, our goal is to let mod of g of t be less than epsilon. That's sort of the goal. So let's do a little bit of algebra to make it happen. So let's simplify g of t carefully. Let me do it this way. And that will give us that mod of gt equals to mod of 4t, which is 4 times the mod of t. And we need to make this guy to be less than epsilon. Let me change all of this to the yellow color. Well, that's rather awkward and embarrassing. It's fine. So let's do it this way. For mod of t, we want to be less than epsilon, so mod of t will be less than epsilon over 4. We want this to be the case. We don't want this to be the case, my apologies. This whole thing will be less than epsilon, based on our calculation. What we want is that this guy be less than epsilon over 4. So we'll choose delta to be epsilon over 4. Because epsilon over 4 is the value that mod of t must be strictly less than. Alright. Great. Let's keep going. That's number 3 on the problem set. We've got a few more to go. I have no idea how much time we're gonna take, but it's gonna be fine. Let's take limit as x approaches 5 of 2x plus 1 equals to 11. I should have done that in white. And once again, we're gonna use the substitution x minus 5 approaches 0, so that means that this will become t and x will be 5 plus t. So we're gonna take the limit as t approaches 0, not 2 times x, but 2 times 5 plus t plus 1. We'll take all of this minus the right hand side. Ideally that gives us a 0. We'll call this whole expression g of t. So fix epsilon bigger than 0, choose delta when 0 less than mod of t less than delta. Ideally, we want to let mod of g of t be less than epsilon. So let's do a bit of algebra. And I like to partition my space so that I can do the algebra on the right hand side. So g of t is going to be this whole expression. Let's do some algebra. And that gives us mod of g of t equals to mod of 2t, which is 2 times of mod of t. And once again, we want to make this be less than epsilon. So let's solve that right there. How can we force this to be epsilon? We can make this epsilon if we were to divide by 2 on both sides. And so we need mod of t to be less than epsilon over 2, which means we can choose delta to be epsilon over 2. We're in for a long treat, so buckle up. Alright, next question. Keep drawing the questions in yellow color. Kinyak, watch it, white color. So we're gonna calculate the limit as x approaches 8, half times x minus 3 to give us not 4, 1. And we can make the substitution. I think we are starting to get the hang of it, but roughly speaking, x minus 8 will approach 0, this will become t, which means that x equals to 8 plus t. So now we take limit as t approaches 0, half of 8 plus t minus 3, this entire expression minus 1 should approach 0. So we'll call this expression g of t, fix epsilon bigger than 0, choose delta to be found later on when 0 is less than mod of t less than delta. We ideally would like mod of g of t to be less than epsilon. So let's go on a hunt. G of t by algebra will be this expression. I believe there is a bracket missing. No, that looks fine. There we go. This will be half of t. So therefore, mod of g of t will be equal to mod of half of t, which is half times mod of t. And we need to make this less than epsilon once again. How can we make this less than epsilon? We'll do that and we'll solve for t to be less than 2 epsilon. So we need t to be less than 2 epsilon, and therefore we make delta 2 epsilon. Alright. And this is the rudimentary aspect of the epsilon-delta proof. We can keep going. Question 6. Limit as x approaches 12 of 1/4 x plus 5 equals to 8. So we want to rewrite this in this manner. X approaches 12, so x approaching, well, x minus 12 approaching 0 gives us t. And therefore x will be 12 plus t. So we'll make the substitution t to 0 of 1/4 12 plus t plus 5 all minus 8. This whole thing should be equal to 0. We can repeat the structure. And we once again would like, let's call this g of t. We would like mod of g of t to be less than epsilon. Let's keep going. Let's simplify g of t algebraically. this is a typo error here. So g of t is 1/4 t. And we want this to be less than epsilon once again. So let's solve for mod t. And we need this to be less than 4 epsilon. So therefore, we'll choose delta to be 4 epsilon. Right. This is actually a complete epsilon-delta proof if you're wondering. So we actually do establish what we are looking for. Alright, problem number 6. Down in the bag. Let's go. Problem number 7. I think everyone can see the screen this time around because I've edited the settings so that I don't have to worry about bad cropping and whatnot. Let's prove this guy. Limit as x approaches 3 of 5 minus 2x being equal to -1. Since x approaches 3, we will now use the substitution x equals to 3 plus t. And ideally, this whole thing will simplify to 0. Once again, we'll call this g of t. Fix epsilon bigger than 0, choose delta, so that when 0 less than mod of t less than delta, we would like g of t, the absolute value, to be smaller than epsilon. Let's calculate g of t for the 20 millionth time. And we're only on question 7, so this is gonna be fun. So g of t is negative of 2t, and we might be a bit concerned with the negative sign, but let's just see what happens. If we pull out the negative 2 out of the modular sign, the negative 2 becomes flipped to positive 2, which means we don't actually have to worry about the minus signs at all. We want this to be less than epsilon, so we solve that again. And therefore, because of that, we will choose delta to be epsilon over 2. And we're done. Some of you might already see a shortcut to all of this working, and you probably can even prove that shortcut. But for the sake of practice, we're just gonna keep going. Alright, let's calculate this guy. Limit as x approaches -1 of 8 plus 7x equals to positive 1. Since we're going x to -1, let's just write it down here. So it's x minus -1 approaches 0. We'll let x be equal to -1 plus t. So that will be our substitution. This whole expression -1 should give us 0. Let's call this g of t. Fix epsilon bigger than 0. Choose delta, so that when 0 is less than mod of t less than delta, we would like mod of g of t to be less than epsilon, and we can slowly continue the hunt. And we will get g of t equals to 8 plus 7 minus 1 plus t minus 1. There we go. 8 minus 7 plus 7t minus 1. So g of t is 7t. And we can allow this to be smaller than epsilon via solving for t. So delta will be epsilon over 7 because we need mod of t to be smaller than epsilon over 7. That is question 8. Alright, we're gonna be very soon 1/10 of the way there, so that feels great. We need to find this limit of 2 plus 4x all over 3 as x approaches 1. That should equal to 2. Since x is approaching 1, we will let the substitution be x equals to 1 plus t. We take this whole thing minus 2. This should give us 0. We will let this be g of t. We'll fix epsilon bigger than 0, choose delta. Then when 0 less than mod of t less than delta, we would like mod of g of t to be less than epsilon. Let's do some algebra. Well, not very convenient. So g of t is 4/3 of t. And we need to force this to be less than epsilon. I think we can do it. We will choose, well, delta to be 3/4 epsilon. Alright. Whew. Okay, let's go. Let's keep going. There are 100 epsilon delta questions. Part of me is thinking this might not be able to end well, but it's okay, we'll get there. How do we sort of break down a huge item? One bite at a time. The limit as x approaches -3 of 2 plus 4x over 5 equals to -2. And what that tells us is, since x approaches -3, our substitution will be x equals to -3 plus t. We'll take this whole thing subtracted by -2. We want to get 0. This will be g of t. Fix epsilon bigger than 0. Choose delta this way, so that when mod t is between 0 and delta, we would like mod of gt to be less than epsilon. Let's do some algebra. This is a long calculation. So g of t will be 4 over 5t. And we can force this to be less than epsilon by choosing 4 over 5 mod t less than epsilon. There we go. So we need this to be less than 5 over 4 epsilon. And we're good to go. Sometimes we could guess the delta, but most of the times it's really hard. So usually we just try to reverse engineer what we do need before we substitute in, we choose our deltas. Okay, great. That's 10 questions down in the bag. Alright, now for this next question, we're going to encounter quadratics. So we want to take the limit as x approaches negative 2 of x squared minus 1 equals to 3. And of course, the quadratic element makes it a little bit not as straightforward. However, we could probably still apply the same strategy. So once again, as x approaches minus 2, we're going to make the substitution x equals to minus 2 plus t. Let me just write it down here. What am I doing? This is the substitution t. And x is equal to minus 2 plus t. So for those of you who are new here, the strategy is to replace x with the thing it's approaching to plus t, so that all of our calculations will be in terms of t instead of x. And usually this makes the expression much cleaner and much more user-friendly to calculate. So instead of, in this case, since x approaches negative 2, we know that x plus 2 will approach 0. So we'll let this x plus 2 be t, and x must be minus 2 plus t. So we'll make the substitution. This is, since the expression approaches 3, we can think about it as the expression minus 3 approaching 0. By introducing all these zeros here, it definitely will make the calculation a lot cleaner and predictable, more predictable. So we're going to call this g of t, and we'll fix epsilon bigger than 0. We need to choose delta, so that if the inputs are constrained by this delta, we would love it if mod of g of t is to be smaller than epsilon. This is what it means for the limit to be that value using the epsilon-delta definition. Let's go on a hunt. Let's simplify g of t. So g of t would be minus 4t plus t squared. We can do a bit of factorization, because we could factor the t to get t times t minus 4. So we can factor that. And when we factor, the modulus of a product is the product of the moduluses. So we're good to go. On the right hand side, we have this t minus 4, and it's not as convenient as we hoped, because, well, we can bound t, but we can't really bound t minus 4 as much as we want to. So we will employ this trick called the triangle inequality, which basically says that the modulus of a sum is always smaller than or equals to the sum of the moduluses. And in fact, because of how moduluses work, minus sign works well too. The point there being is that we can employ the triangle inequality here, so that mod of t minus 4 is now bounded by mod of t plus 4. At this point in time, there are a few things that we could attempt, but one possible way to attempt this is we want this whole expression mod of gt to be smaller than epsilon. So why not let's bound this guy first. Let's bound this guy by a fixed number, and if we can do that, that'll be great. So for convenience, since it's the easiest, let's just bound it by mod of t less than 1. This will allow this expression to be smaller than mod of t times 1 plus 4, which is 5 mod t. So we've already stipulated one condition. We need mod of t to be, on the one hand, smaller than 1. On the other hand, we still have this whole expression g of t being eventually bounded by 5 times mod of t. And that tells us we want to still bound it by epsilon at the end of the day. So how do we go about doing that? we will solve for modulus of t. So on the one hand, we need t to be smaller than 1. And on the other hand, we also need it to be smaller than epsilon over 5. We know that mod of t will be smaller than delta. So which delta should we choose so that mod of t will be smaller than both 1 and epsilon over 5? Let's just choose delta to be the smaller of the two. And if this sort of gives us a bit of worries that, oh, wait a minute, what if mod of t sort of equals to delta, blah, 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 so on and so forth, let's just ease our consciences and put a half there. That way, this will definitely be smaller than half of 1, which is definitely smaller than 1, and this will definitely be smaller than half of epsilon over 5, which is strictly smaller than epsilon over 5. With these conditions, we have shown what we wanted. We've shown that mod of g of t will be smaller than epsilon. We fixed epsilon bigger than 0, we chose delta, so that when we constrain the inputs to be smaller than this delta, the outputs will be constrained by epsilon. We're good to go. If you want to see a proof as to why this trick works, you can check out the link in the description below. Let's do problem number 12. This will be limit as x approaches 2 of x squared plus 5 equals to 9. So once again, we will employ our trick. Since x approaches 2, we will substitute x equals to 2 plus t. This will be 2 plus t. And we'll take this whole expression subtracted by 9. We'll call this g of t. And we will write in our epsilon delta structure. We would like mod of g of t to be smaller than epsilon. Let's do a bit of algebra on mod of g of t. And we can even do some factorization at the very end. So mod of gt is precisely mod of t times mod of t plus 4. We can employ the triangle inequality like before. Because it's easier to control the individual terms rather than the term as a whole. And we can make it convenient by choosing mod of t smaller than 1. We want this to be smaller than epsilon. So what we need in order to get this approach is to get 5 mod t less than epsilon, which means that mod of t is less than epsilon over 5. So we need mod of t on the one hand to be smaller than 1. On the other hand, it has to be smaller than epsilon over 5. So we will choose delta to be the smaller of the two. And if you want to ease your conscience, you can just add the 1/2 over there. That way you never have to worry about mod of t at all. And that's it. Alright, problem 13. We're taking the limit as x approaches 5 of the quadratic expression. Since x approaches 5, we would let x equals to 5 plus t. And there's a 10 on the right side, so let's pull it over. we want this all to be equal to 0. Or we want the limit to be 0. Let's call this GT. Fix epsilon bigger than 0. Choose delta so that when 0 less than mod of t less than delta, we would like mod of g of t to be less than epsilon. So let's do that. G of t, let's simplify this by algebra. So this simplifies to t squared plus 7t, which we can factorize. So let's do some calculations here. Mod of gt will be equal to mod of t times mod of t plus 7. Let's apply the triangle inequality. That was rather awkward and embarrassing. My apologies. And now we can stipulate that mod of t is less than 1. And we want this to be smaller than epsilon. So what we need in order to achieve this result is that mod of t is smaller than epsilon over 8. So we need mod of t to be smaller than 1, and we need mod of t to be smaller than epsilon over 8. We will choose delta to be the smaller of the two. And once you're comfortable and you don't want to put the half there, totally fine. Yep, that's the proof for this question. Alright. Question 14. The limit as x approaches 4 of x squared plus x equals to 20. We will let x be equal to 4 plus t, because we are approaching 4, so let's consider 4 plus t. We will let this be g of t. Fix epsilon bigger than 0. Choose delta equals to whatever, so that when mod of t is less than delta, we would like mod of g of t to be less than epsilon. So let's do some algebra. I just realized there was that dotted function. That's pretty cool. Let's do some algebra here. So that g of t is actually t times t plus 12. That's really ugly. Let me rewrite that. We can split this up using modular symbols. And mod of t plus 12 can be upper bounded by the triangle inequality by mod of t plus 12. We can, out of convenience, let mod of t be smaller than 1 here. Eventually, if we choose delta, that will happen. Oops. And we want this to be smaller than epsilon, so we will now let mod of t be smaller than epsilon over 13. So this will allow us to choose delta to be the smaller of 1 and epsilon over 13. And we are done. This is going to be my first 100 handwritten document in a single day. Let's calculate this guy. The limit as x approaches 2 of x squared minus 5x plus 6 should equal to 0. We are approaching 2, so we will let x equals to 2 plus t. Now this should equal to 0, the best case scenario. Call this g of t. I shouldn't really do this. This is a bit misleading. Looks like a divide symbol. I'll just put the arrows there. So fix epsilon bigger than 0. Choose delta so that when 0 less than mod of t less than delta, we would like mod of g of t to be less than epsilon. So here, let's do some algebra. So this simplifies to t squared minus t. There we go. And we can calculate mod of g of t equals to mod of t times mod of t minus 1. This will allow us to upper bound the second term using the triangle inequality. And we can upper bound the second term by 1 by stipulating that mod of t is smaller than 1. And we can upper bound this whole thing by epsilon by stipulating that mod of t is less than epsilon over 2. So we need mod of t to be less than 1 and epsilon over 2. So we take the minimum. Alright, we are making non-trivial progress here. That's pretty good. Okay, so we have this expression. We have a lot more questions to go. We have 40 on this. That's non-trivial. Okay, let's go. We're going to find the limit as x approaches 3 of x squared minus 5x plus 6 equals to 0. I'm going to get lazy with my x's here and just use the usual crosses in this manner. And we want to rewrite this as 3 plus t, in the sense that x equals to 3 plus t. So we'll call this guy g of t. Fix epsilon bigger than 0, choose delta equals to our term, so that when this guy holds, we would like mod of g of t to be smaller than epsilon. Let's do some algebra, just like before. And that is our simplification. We can even factor the t, so that mod of gt is equal to mod of t plus 1. We can bound the second term by the triangle inequality, and we can bound that by 1 if we were to stipulate that mod of t is smaller than 1. We could stipulate that mod of t is smaller than other numbers. That's fine. 1 is purely out of convenience. Okay, 2 mod t. We can now stipulate this to be smaller than epsilon, provided that mod of t is smaller than epsilon over 2. We need mod of t to be smaller than 1 and epsilon over 2. So that is precisely our answer. Let's go to question 17. Woo. to be fair, we are making pretty good progress. That basically gets us to about 20 questions. So we should be done in 5 hours, hopefully. 2x squared plus 3x plus 1 equals to 6. My brain just stopped working there. I don't know if you guys have that, but there's that. Since x approaches to 1, we're going to use the substitution x equals to 1 plus t. And we want to show that g of t will approach 0. So we'll fix epsilon bigger than 0. Choose delta so that when the inputs are constrained, we would like the outputs to be constrained by epsilon. That sort of frames what we're talking about, so that really helps. Let's do some algebra. So g of t is this whole expression. So we can expand the first term using a squared plus 2ab plus b squared. The second term follows by opening up the brackets, 3 plus 3t. And we have a constant, we have two constants over there. So if we simplify this, the constant terms will be 2 plus 3 plus 1 minus 6. So that's 0. The linear term, the terms involving t, will be 4t plus 3t, so that's 7t. And the t squared term is actually plus 2t squared. So we're going to get t times 2t plus 7. So it's a little not as straightforward as the monic polynomials, the monic quadratics, but it's fine. Mod of g of t will be equal to mod of t times mod of 2t plus 7. We can bound it by the triangle inequality because mod of 2t plus 7 is bounded by mod of 2t plus 7. We can even bring the 2 out, so that's actually 2 mod t plus 7. Let's make the bounds over there. And we can bound mod t by 1, just like before. And we can bound 9 mod t with epsilon by bounding mod of t by epsilon over 9. So we can choose delta to be the smaller of the two. And if you would like to put a half in front of all of that, that's fine too. Alright. We're at question 17. Let's go to question 18. We want the limit as x approaches -1 of the polynomial, the quadratic polynomial. We want this to be equal to 0. And let's make the substitution. Since x approaches -1, we would make the substitution x equals to -1 plus t. This will be our g of t. We will fix epsilon bigger than 0, choose delta, so that under the stipulation, we would like mod of g of t to be smaller than epsilon. Let's keep going. Do some algebra. And this could take some time, so patience is key. The constant terms will be 2 plus -3 plus 1. That's 0. The linear terms will be -4t plus 3t, so that's -t. and the quadratic term will be 2t squared. So we can factor the t to get t, 2t minus 1. So mod of g of t will be mod of t times mod of 2t minus 1. We can bound this using the triangle inequality, because of mod of 2t minus 1 will be smaller than or equals to mod of 2t plus 1, and we can even pull the 2 out. But so mod of 2t plus 1, and we can even pull the 2 out. So this will be smaller than or equals to this guy. T can be bounded by 1. And 3 mod t can be bounded by epsilon. But how do we do that? We set mod of t to be smaller than epsilon over 3. So we have these two conditions here, and they'll tell us that delta should be the smaller of the two. Alright, let's keep going. Problem 19, we're going to take the limit as x approaches 1 of 4 plus x minus 3x squared being equal to 2. Since x approaches 1, we'll use the substitution x equals to 1 plus t. And we want this whole expression, minus 2, to approach 0. This will be our g of t. Fix epsilon bigger than 0, choose delta, such that when the inputs are constrained, we would like the outputs to be constrained as well. Let's do some algebra. This might take some effort. Well, this is awkward and embarrassing. Let's try that again. So the constants for 1, minus 3, and minus 2 will all add up to 0. The linear term, t and negative 6t, will add up to negative 5t. And the quadratic term will be negative 3t squared. So we can now factor the t and the minus sign, because why not? So mod of gt is equal to mod of this expression mod of t, or rather mod of negative t, can be replaced by mod of t, and mod of 3t plus 5 can be bounded using the triangle inequality. So we're gonna get 3 mod t plus 5 bounded this way. We can bound t by let's shake it up a bit. We could use 1, but let's just, for the sake of entertainment purposes, let's say mod of t is less than 1/3. Okay, let's just show that it still works. So this will be bounded above by mod of t and 3 times 1/3 plus 5. So this will be 6 mod t. And we can upper bound this by epsilon if we were to stipulate that mod of t is smaller than epsilon over 6. So this allows us to choose delta to be the smaller of these two stipulations, the smaller of 1/3 and epsilon over 6. So we can use other bounds at this step if we wished, as long as the remaining bound still helps force mod of gt to be smaller than epsilon. Alrighty, 20. And we are 1/5 of the way there. That actually feels pretty encouraging. Okay. So we want to, since x approaches minus 3, the substitution will be x equals to minus 3 plus t. We take this whole thing minus negative 25, and hopefully this goes to 0. This will be gt. We'll fix epsilon bigger than 0, choose delta, and we would want, rather when the inputs are constrained, we would like mod of gt to be smaller than epsilon. So let's go this way. Mod of g of, well, let's not do mod of g of t, let's just simplify the algebra, the vanilla gt. Let's go. This could take some time, so we might want to expand this slowly. For the first term, it's actually 5. The second term will be minus 3 plus t. The third term is going to be minus 3 times minus 3 plus t all squared. So there will be a squared plus 2ab plus b squared. And finally, we have a minus negative 25. So there's our expression over there. The constants will add up to 5 minus 3. The constants 5, negative 3, negative 27, and 25 will sum to 0. The linear terms will be t plus 6t. That's 7t. And the quadratic term will be minus 3t squared. So let's pull out a negative t. So then we get 3t minus 7 on the inside. And, well, brackets here. So we're going to even do it this way. Mod of g of t will be equal to mod of minus t 3t minus 7 equals to mod of t 3t minus 7. So then in one single step, I can write mod of gt equals to mod of t 3t minus 7. And we can apply the triangle inequality. To get 3 mod t plus 7. We can bound t by 1 to get 3 times 1 plus 7. So that gives us 10 of mod t. And we can bound this by epsilon by stipulating mod of t less than epsilon over 10. So delta has to be the smaller of these two guys. And if delta has to be the smaller of these two guys, we'll take the minimum of 1 and epsilon over 10. Alright, we are 1/5 of the way there. If you are new here, strap on and enjoy, and it's gonna be fun. The questions are in the description, so you can knock yourself out with that if you so choose. And we are gonna continue with question 21. So we need to calculate the limit as x approaches 2 of x cubed minus 1 equals to 7. So we need to establish this limit using epsilon deltas. And the trick here is, rather than work in x, we observe that x approaching 2 means that x minus 2 approaches 0. So we're going to let this be denoted by t, and therefore x will be equal to 2 plus t. So we can reformulate this limit in terms of t, and usually when that is the case, the bounding of the terms is a lot clearer and there's a lot less things to sort of wrap our heads around. This substitution does a lot of work for us. So let's make the substitution. Whenever we see an x, we can replace it with t, in the sense that, okay, if x approaches 2, then t must approach 0. And here we have x cubed, but instead of x, let's just replace it with 2 plus t cubed minus 1. And when this expression approaches 7, we can actually check that the expression minus 7 must approach 0. The proofs are in the notes, so you can check them out in the description box below. And we are now going to try to control this term. So what does the epsilon delta definition require of us? We need to fix epsilon bigger than 0, and we need to choose some delta judiciously so that when the inputs are constrained by this delta, hopefully the outputs will be constrained by epsilon. That's the key idea of the epsilon delta proof. A lot of results in higher level mathematics use this idea, so it's a useful idea to have at the back of our minds. But by doing this way, we can actually make things more simple for us. So let's expand g of t. Now, when we expand g of t, we notice that there is a cubic term over here. Oops. We actually notice there's a cubic term here, so we can expand it using the binomial theorem, or by just slowly opening up using the table method or whatnot. In this case, I'm going to use the binomial theorem, and that tells us that to expand a binomial, let me just write it here, we're going to first take 3 choose 0 times the second term to the third power plus 3 choose 1 times the second term to the second power and the first term to the first power. Then we'll follow by 3 choose 2 of 2 to the 2 t, and finally 3 choose 3 2 cubed, and no more t's. So the powers of t go up and the powers of 2 actually go down until you're left with a total of 3 plus 1 equals to 4 terms. Now 3 choose 0 we can type into our calculators, or if you are aware of some combinatorial results, actually equals to 1. So that's just t cubed. 3 choose 1 is just 3, so 3 times 2 is 6. 3 choose 2 is 3, so 3 times 2 squared, that's 3 times 4, that's 12. And 3 choose 3 is 1, so that gives us 2 cubed, which is 8. So we expand this whole expression to get t cubed plus 6t squared plus 12t plus 8. This is done by expanding this using the binomial theorem. And we minus 1 minus 7 to get minus 8. Oops. Minus 8. So all of that sort of cancels out. The 8s cancel out and we are left with this polynomial in t. We can factor a t. And what we have here is that g of t equals to all of that. It looks kind of long, but it's actually not as crazy as it seems. Because this is a modulus of a product, which means we can equate this to the product of the moduli, whichever. For this second term, we can upper bound it using the triangle inequality, and the triangle inequality does hold even if there are more than 2 items inside the modular symbol. So what does that mean? It means that the triangle inequality states that modulus of a plus b in the context of 3 items will be smaller than the sum of the moduluses. So in our context, we're going to get mod of t squared plus 6t plus 12 smaller than or equals to the sum of each of these items. We can even pull the 6 out and rewrite mod of t squared as mod of t all squared. So this will be upper bounded by mod of t times mod of t squared plus 6 mod of t plus 12. And at this stage, we can choose, well, we want to bound this whole right term, so let's just upper bound this guy by 1. I mean, we can, we have the freedom to choose a delta, so let's choose delta, among other things, so that one of the conditions that mod of t satisfies is mod t less than 1. This helps us to control this second term. And a little bit of mental sums here will give us, will give us 19 mod t. We can force this to be smaller than epsilon by taking mod t less than epsilon over 19. Whoops, made a careless mistake there. And we need our mod of t to satisfy these two conditions. So let me write it here. We need mod t to be less than 1, and we need mod of t to be less than epsilon over 19. What that means is that whatever our delta is has to be smaller than 1, and it has to be smaller than epsilon over 19. So we are going to choose delta to be the smaller of the two. And if you're a bit uneasy that, wait, what if the modulus of t will equal to these numbers? Let's just throw in a half right there. That way, delta will surely be less than 1 without any debate, because it's smaller than half of 1, so it has to be smaller than 1. And it has to be less than epsilon over 19, because it's smaller than half of that. So delta will definitely be less than epsilon over 19. The point, therefore, is that mod of t can be controlled by 1 and epsilon over 19, and that actually gives us the conclusion that we are looking for, that g of t is smaller than epsilon. Let's keep going. Example 22. We're going to get the limit as x approaches 2 of x to the 5 plus 2 equals to 34. This looks kind of not fun, because we are going to have to do a little bit of algebraic manipulation. I think we can do it, but I think there might be a slightly more efficient approach. So I'm gonna try to go about with that, because I like to tell people math people are like the laziest people on earth. So let's just go ahead and let's allow x to be 2 plus t. We take this whole thing minus 34, and ideally this goes to 0. So this will be g of t. We'll fix epsilon bigger than 0, choose delta, so that when the inputs are constrained by delta, we would like the output to be constrained by epsilon. So the first thing to do is do a bit of algebra, and you can see that the algebra here gets a little bit nasty. Well, this could be a problem, right? Now, I'm gonna cheat a little bit here, okay? So we're gonna cheat. So this will be 2 to the 5, 2 plus t to the 5 minus 32. And we know that we have a binomial expansion for this. We don't actually want to expand every single term out, so that will take quite a long time. But we do know what the first term is. The first term is 2 to the 5th. And the next few terms are basically summations of the form, of items of the form 5 choose k, 2 to the 5 minus k, t to the k. I think I did the previous binomial theorem wrongly, but it still gets the same answer. And we are going to sum from k equals to 1 all the way till 5. So what we are doing here, we are expanding the binomial expansion, but not completely. We're just going to write it in this summation formation, because the 2 to the 5s will cancel with the 32, because 2 to the 5 is 32, And we are going to be left with this expression. We are left with this expression, and it might not be obvious, but we can actually factor a t, because we are actually adding up something times t plus something times t squared plus something times t cubed. So we can actually factor a t over here. So that this guy becomes t to the power of k minus 1. This whole expression, I'm going to give it a new name. We're going to call it the p of t. This is going to be a polynomial of t. And we can write g of t in this manner. Mod of g of t is equal to mod of t times mod of p of t. Just like before, we could try to bound mod of pt, but let's make an interesting observation here. We are bounding p of t by bounding a sum of items. Right? Bounding a sum of items. And the triangle inequality allows us to upper bound this by the sum of the moduluses of the items. And this expression, interestingly enough, is actually going to be p of mod t, because we can just substitute mod t into the expressions. Everything inside is positive, so we don't have to worry so much. What that means is that we can upper bound this guy by p of mod t. And if we look at this expression very carefully, we can even, if we were to stipulate mod of t to be 1, less smaller than 1, we can upper bound this by mod of t. Well, we can strictly upper bound this by mod of t times p of 1. Because the mod t's will all be smaller than 1, so the entire expression on the right will be smaller than if you were to substitute 1. And we don't have to worry, p of 1 in this formulation definitely would be positive. So we can even bound this guy to be mod of t times epsilon over mod of t to get epsilon. Well, not epsilon over mod of t, my apologies. We can bound this guy to be smaller than epsilon if mod of t times p of 1 is smaller than epsilon, which means that mod of t is smaller than epsilon over p of 1. So by defining p in this way, I've sort of cheated because I never really gave you the actual number, but you could calculate it in a computer. It will be positive, and we don't have to worry about this expansion. We will get delta. We will make sure that mod of t is smaller than 1 and smaller than epsilon over p1. So delta will be the minimum. Whoops, let me do that. Minimum of 1 epsilon over p1. You can put a half there if you want some assurance. So this is how I cheat, and you are allowed to cheat. This is a legitimate approach. Let's do 23. We need the limit as x approaches -2 of 2x cubed minus x equals to -14. We will once again rewrite this, since we are approaching -2. We will rewrite this to be x equals to -2 plus t. Minus -14 equals to 0. So we will let this whole thing be g of t fix epsilon bigger than 0, choose delta, so that when we restrict the inputs, ideally mod of g of t will be less than epsilon. Let's do a bit of algebra. Since it's power 3, I'm not as worried about expanding power 3s, but I do get worried when we need to start expanding power 5s onwards, like the previous question. The joke is that any number bigger than 5 is a pretty big number for a math person. And it has to do with Galois theory and all of that, but let's not go there. Whoops. Let's do some algebra, again, for the 20 millionth time. Well, not very convenient. You know what? I think I need to slowly expand this. I'm gonna try that again. Try that. There we go. That's more like it. So this will simplify too. Whoops. Okay, that seems more like it. And the constants will go to 0. The linear term will be 2 times 12. 2 times 12t minus t, so that's 24t minus t, that's 23t. The quadratic term will be minus 12t squared. And the cubic term will be 2t all cubed. What that means is that we're going to get modulus of g of t will be equal to this guy. We can factor the t as per usual. And we can upper bound the second term using the triangle inequality. And we can even upper bound the second term via, mod t less than 1. So on the right side, we're getting something a little bit complicated, but still doable, because 23 plus 12 is 35, 35 plus 2 is 37. And this will be smaller than epsilon when mod of t is less than epsilon over 37. We need our mod t to satisfy these two conditions. So we will now choose delta to be the smaller of 1 and epsilon over 37. Let me write that more clearly in that way. Well, these are the cubic types. It takes a bit more effort to expand, but can be done. I would still rather expand than factorize, because to factorize cubics might involve quite a bit of careless mistakes. So let's just do that. Let's do 24. Limit as x approaches -1 of x cubed plus 5x equals to minus 6. We'll substitute x with -1 plus t. We'll take that all subtracted by -6. That was redundant. There we go. We will let this be g of t. We'll fix epsilon bigger than 0. Choose delta equals to whatever, so that when the inputs are constrained, we would like mod of gt to be smaller than epsilon. So let's keep going. It's getting pretty exhausting, but we can do it. We can do it. If you're new here, just chill along and study along with me, right? Because why not? This will simplify to... this could take a while. So the first terms will be minus 1 minus 5 plus 6. That goes to 0. The second term will be 3t plus 5t, so that's 8t. The third term will be negative 3t squared. The fourth term will be t cubed. Gosh. Try that again. T cubed. There we go. And we can factor the t. So, mod of g of t will be mod of t mod of 8 minus 3t plus t squared. We can upper bound this by we can upper bound the right hand stuff by the triangle inequality once again. And we can bound this by setting mod t smaller than 1. This will simplify to 12 mod t, which can be made smaller than epsilon by setting mod t smaller than epsilon over 12. So we need to factor in these two conditions, and we'll get delta to be the minimum of 1 and epsilon over 12. We are at problem 24. Okay, really nice. And let's go to problem 25. Now we're dealing with a square root problem. So we'll take the limit as x approach 3 of root of x plus 1 equals to 2. We want to find this limit, or rather we want to prove this limit using epsilon deltas. So the first trick is to make the observation that x approaching 3 is akin to x minus 3 approaching 0. So we can make the substitution x minus 3 equals to t. So that way, we can make the substitution x equals to 3 plus t. And why do we make this substitution? Because in practice, the manipulations get pretty easy once we do this. So let's make the substitutions. Instead of x approaching to 3, we're now getting t approaching to 0. And instead of square root of x plus 1, it'll be square root of 3 plus t plus 1. And if this entire expression approaches 2, then the entire expression minus 2 ought to approach 0. If you want to see a proof of why this works, you can check it out in the description box below. The questions are there as well, so feel free to download and attempt them as your own practice. Now, let's do some simplifications. This guy is going to be, we're going to call this g of t. And the epsilon delta proof requires us to do this. For any epsilon bigger than 0, we are required, there we go, to find delta. Well, it's our job to find a delta so that when we take 0 less than mod t less than delta, ideally, mod of g of t will be less than epsilon. So this is the goal. And how do we find such a delta? We usually do a little bit of algebraic manipulation to get g of t equals to square root of 3 plus t plus 1 minus 2. We'll do some simplification over here. So this will be 4 plus t minus 2. And at this point in time, it feels a little bit challenging to sort of bound t, because the square root isn't exactly the most friendly compared to the polynomial types. So what we will do as a trick is to rationalize the denominator. Well, there's no denominator here, but we will multiply by the conjugate. So here's the trick. Let me do it this way. To get rid of the square root, the key idea is to use the conjugate approach, like this, so that ideally we can bound the lower terms in a very nice way. On the top, we're gonna get a difference of squares, and on the bottom we're gonna get this guy. So that would simplify to 4 plus t on the top minus 4. The bottom will remain the bottom, nothing to fear there. So this simplifies to t over all of that on the bottom. Once we have that, we can now say that modulus of g of t is smaller than mod of t over mod of root 4 plus t plus 2. And our desire is that we can bound this whole thing, once again, by epsilon. This is our goal. We're trying to work towards that goal. At this point in time, we must ask ourselves the question, what can we actually do here? The first thing to note is that on the bottom, we're getting square root of something plus 2. So square root of something is always non-negative, right? This guy is always non-negative, which means that square root of something plus 2 is always bigger than or equal to 2. So when we were to divide or take the reciprocal, it will always be bounded by a half. So we can write this not as mod t divided by this expression, but by 1 over this expression times of mod t. This will make the bounding by a half pretty obvious. And once we can bound it that way, we can bound this whole thing by epsilon simply by solving this inequality. So in fact, we have the condition mod t smaller than 2 epsilon. However, we still have to take care of one little business over here. We actually need to make sure that everything on the inside of the square root has to be positive. That way, we don't have to, that way we can actually talk about square root of something. So let's just make sure that everything is well defined. And let's just say that, let's just go ahead to solve 4 plus t being bigger than or equal to 0. We allow 0, it's fine. But t has to be bigger than or equal to minus 4. Right? On the other hand, we do know that this implies that negative delta is smaller than t is smaller than delta. So we have a bunch of conditions to take care of. Firstly, we actually need the condition that mod of t is smaller than 2 epsilon. Secondly, we need the condition that mod t is bigger than minus 4. Or rather, t has to be bigger than minus 4. So what condition would help us achieve that goal? Well, if we think about it, this can be achieved by t being bigger than minus 4. In other words, if delta is a number that's smaller than 4, right, then t will be definitely bigger than negative 4. On the other hand, we need delta to be, or rather we need mod of t to be smaller than 2 epsilon. So why not, or rather let's do it over here. We need this mod of t to be smaller than 2 epsilon. So we can take delta to be the smaller between 4 and 2 epsilon. And we can even take half of that just so that everything is really as small as it gets. By doing it this way, if delta is smaller than 4, then t being bigger than negative delta will be bigger than negative 4. So let me write it out. Let me this way. Right? If delta is smaller than 4, then this guy would definitely be bigger than minus 4, and the non-negativity condition will definitely be satisfied. On the other hand, delta being smaller than 2 epsilon will allow the bounding condition to be satisfied, which allows us to get this conclusion. We this allows us to get this conclusion. And if we were to read this proof, we actually do get, for any epsilon, we have found a delta such that when the inputs are constrained by delta, the outputs will be constrained by epsilon. So let's look at the next exercise. The exercises are all in the link in the description, so you can take a look over there. So we take limit as x approach to 5 of root of 2x minus 1. This will be equal to 3. Once again, before we do any simplifications, we're going to make the substitution. Since x approaches 5, let me write it over here. Since x approaches 5, x minus 5 will approach 0. So we'll let this be t. X will be 5 plus t. And we can rewrite everything in terms of t. We'll take limit as t approaches 0 of 2 times 5 plus t minus 1. Once again, since everything approaches 3, ideally everything minus 3 approaches 0. Proof is in the notes. So let's do some simplifications here. Let's simplify this whole thing. This is called g of t. We'll fix epsilon bigger than 0 and choose delta so that when 0 less than mod of t less than delta, in the ideal situation, mod of g of t will be less than epsilon. That's what we hoped. This tells us that we need g of t to be this guy. And we can do a bit of algebra to simplify everything. Let's do some algebra to simplify everything. So we have this expression, and it once again is not easy to work with this expression. So what we will go ahead to do is to rationalize the denominator. Part of me actually thinks that we can use this trick. Part of me thinks we can do this trick. I mean, you definitely don't get equality, but part of me thinks that this trick is a legitimate one. And I think this is a legitimate inequality. I think we're allowed to split up the square root in this manner. I think we're allowed to do this. So let me try that again. Let me establish that this result actually is legitimate. So root of 9 plus, well, let's check. So let's just do a shortcut here that we can actually upper bound in this way. Okay, there's a I would love to upper bound it this way, but unfortunately there might be some zero difficulties to work with, so I think I won't risk it that way. We're just gonna do the rationalizing of denominator. That way we don't have to worry about zero denominators and whatnot. So let's rationalize. The numerator will be 9 plus t minus 3 squared, because it's a difference of, it's a product of, how do you describe it? Whatever, the numerator will be a plus b, a minus b. So that will simplify to a squared minus b squared. Difference of squares, 9 plus t minus 3 squared. So this simplifies to t over root of 9 plus t plus 3. This tells us that modulus of g of t can be written once again as 1 over all of this guy times modulus of t. We see that this whole thing will be upper bounded by 1/3 because the denominator is 3 plus a positive term. So it has to, 1 over that has to be smaller than or equal to 1 over 3. And this will be smaller than epsilon if we stipulate that mod of t is less than 3 epsilon. On the other hand, we need to make sure that 9 plus t is non-negative. So we need to make sure that t is bigger than or equal to minus 9. Which means that we'll need t to be bigger than minus 9. So on the one hand, we need okay, got it. We need t to be bigger than minus 9. So this also tells us that if we can make sure that mod of t is smaller than 9, then we will get t being bigger than minus 9, we'll be good to go. So we need to make sure that mod of t is smaller than, let me write that again. We need to make sure that it's smaller than 3 epsilon and smaller than 9. So therefore we'll choose delta to be the smaller of 9 and 3 epsilon. And we are good to go. Yes, a middle of day proof stream. It's gonna be 100 epsilon delta proofs. So this is gonna be fun. So 27, let's take the limit as x approaches -1 of root of 6 minus 3x equals to 3. And we are going to, once again, rewrite this as the limit as t approaches 0. Since x approaches -1, we'll make the substitution x equals to -1 plus t. Let me just write it here. And what will we get? Root of 6 minus 3 times -1 plus t equals to 3. We should bring the 3 over so that everything will equal to 0. So intuitively, it makes a lot more sense that we want to make this guy be as small as possible. So let's fix epsilon bigger than 0, choose delta, so that when we constrain the inputs, what are we gonna get? We hopefully can get mod of g of t less than epsilon. So let's do that. G of t will be root of 6 minus 3 minus 1 plus t minus 3. Let's do a little bit of algebra and see what happens. 6 plus 3 minus 3t minus 3. This will simplify to root of 9 minus 3t minus 3. I might be tempted to sort of factor a 3, but it's okay. Let's just do rationalizing of denominator. Can't go wrong that way, right? So let's do that. We will get root of 9 minus 3t minus 3, root of 9 minus 3t plus 3, all over root of 9 minus 3t plus 3. So the idea is to multiply by the conjugate on the numerator, on the denominator and the numerator. The top will be a difference of squares, so that will be 9 minus 3t minus 3 squared. The denominator will stay put. The numerator will simplify to minus 3t all over root of 9 minus 3t plus 3. So that will give us mod of g of t equal to 1 over root of 9 minus 3t plus 3 times mod of 3 minus t, or rather mod of minus 3t, which is 3 mod t, because we can pull out the minus sign. None of that's good. Okay, so what do we have here? We know that the fraction will always be upper bounded by 1/3 because the square root expression has to be non-negative. And the 1/3 and the 3's will cancel out. So we can make t We can make modulus of t smaller than epsilon by just that, right? But once again, we need to check that the expression in the denominator makes sense. In other words, the expression in the square root makes sense. Make sure that it's non-negative. So therefore, we want 3t to be smaller than or equal to 9, t to be smaller than 3, which means that we want modulus of t to be smaller than 3. So we need two conditions. We need this condition and this condition. So what do? We'll take the minimum of these conditions. And that's it. We are making good progress. We're making really good progress here. We're gonna arrive up to question 30 soon. Let's do this. This is question 28. Let's calculate the limit as x approaches negative 3 of the square root of 13 minus x equals to 4. Let's simplify this to the limit as t approaches 0. Since we're approaching minus 3, we'll make the substitution x equals to minus 3 plus t. We take this whole thing minus 4 and ideally this gives us 0. So we'll fix epsilon bigger than 0. We'll choose delta such that when the inputs are constrained by this delta, ideally we get mod of g of t less than epsilon. If you're watching the stream, you realize I'm repeating the same thing 20 times, but it's for the benefit of those who are watching the short form version of this. So let's calculate g of t algebraically. This could take some time. Let's multiply. Let's rationalize the denominator. Oops, what am I doing? I'm multiplying this term on the top and the bottom. The top will simplify to root of 16 minus, 16 minus t, because it's a squared, so that's 16 minus t, b squared, that's 16. So g of t, the modulus of g of t will be the modulus, it'll be the fraction times the modulus of t. It's very nice, it's just a t. It's great. And we can bound this by 1 over 4 because the denominator has to be bigger than or equal to 4. And we can bound this by epsilon by letting mod of t be smaller than 4 epsilon. At the same time, we also need to make sure that everything inside the square root makes sense. So we need to make sure that 16 minus t is non-negative, which means that t is bigger than, t is not more than 16. And that tells us that mod of t has to be smaller than 16. You could choose a stricter threshold if you wish. So no problem there. We need to make sure that these two conditions are met. So we'll take 4 epsilon and 16. We'll take the smaller of the two. And that's our answer. Whew! Good thing I've got a bit of sugar here. I don't know if the sugar high will run out in a moment. Okay. Problem 29. We're coming up to 2 hours already. That's fast. I've got 100 problems to go. This could take some time. Problem 29. We're going to take the limit as x approaches 9 of root x plus 2 equals to 5. So since we're approaching 9, we're going to make the substitution t approach 0. So that will be root of 9 plus t plus 2. We'll take everything minus 5. We want this to approach 0. So we'll fix epsilon bigger than 0, we'll choose delta, so that when the inputs are constrained, ideally we'll get the outputs be smaller than epsilon, and we need to go on a hunt. Whoops. Whew, this is tiring. Also, shout out to Black Pen, Red Pen if you're watching this. It's inspired from your 100 integrals and all of those videos. So, following your footsteps here, mate. Well, so that's how we rationalize the denominator. We're gonna get 9 plus t minus 3 squared on the top. And we'll get that on the bottom. The top is because of the difference of squares. 9 minus 3 squared, that's just 0. So we'll get this expression, and we can simplify mod of g of t by 1 over root of 9 plus t plus 3 times mod of t. The fraction is upper bounded by 1/3 because the denominator is not smaller than 3. And we can bound this by epsilon by setting mod of t less than 3 epsilon. However, we need to make sure that everything inside the square root still makes sense. So t would be bigger than minus 3, which means that mod of t, we want it to be smaller than 3. We can actually check that if we get mod of t being smaller than 3, we will get t being bigger than negative 3. So we need, well, these two conditions. And that is how we do it. Alright, question 30. Let's keep going. This looks rather irritating, because now we have like negatives and it's pretty disgusting. But we can still approach this using our substitution. So instead of x approaching to minus 9, we'll think of it as t approaching 0, and we'll replace x with minus 9 plus t. We take everything minus 1 equals to 0, and we will let this be g of t. Fix epsilon bigger than 0, choose delta. We want to stipulate the inputs and hopefully get the outputs within epsilon. That would be great. So let's do some algebra. Okay, this will be root of 7 minus t minus 1. This is a little bit bizarre. I'm definitely not used to seeing this expression. I would like to take some time to check my work here. I think I found it. The square root only applies to 9 minus t. So I don't know why I did that. So it should be, the minus 2 is actually on the outside. There we go. This is a lot more intuitively true. So the numerator, we can rationalize the denominator. Oops. Actually, it's more like rationalizing the numerator. But in any case, it's a useful problem-solving technique. So this would get us 9 plus t, 9 minus t minus 3 squared on the top. The bottom is the square root term. The top simplifies to negative t. And what happens there is that mod of g of t is gonna be 1 over root of 9 minus t plus 3 times mod of t. And we can bound the denominator, or we can lower bound the denominator by 3, so we can upper bound the entire expression by 1/3. We can bound this by epsilon if we let mod of t be bounded by 3 epsilon. Let's just make sure that everything in the square roots are legitimate. So we want t to be smaller than 9. In other words, I want mod of t to be smaller than 9. We can choose the stricter condition to imply the weaker condition, so that's fine. Let's choose the smaller of these guys. And that's it. That's that. Alright, it's question 30. Let me take a sip. Whew! This is pretty intense. This is pretty intense. Okay. Alright, let's do the next question. Question 31. And we are going to prove using epsilon deltas that this guy is equal to this. Just like before, we are going to well, if you've watched some of the previous videos, you know we're going to make a substitution. But if you're new to doing epsilon delta proving, the trick to dealing with epsilon deltas in an easy and user-friendly way is to make a substitution. So the trick here is that if x approaches to 1, then x minus 1 must approach, well, awkward, x minus 1 must approach 0. And if x minus 1 approaches 0, we can let this guy be t, so we can make the substitution x equals to 1 plus t. So now instead of thinking of x approaching to 1, we're going to think of the error term t approaching 0. So that way, when you think of bounding error terms, the calculations tend to be a lot more straightforward. So let's just do that. So instead of x, we're going to write this as 1 plus t. And if the entire expression approaches 1, the entire expression minus 1 ought to approach 0. If you'd like to see a proof of this result, it's in the notes in the description box below. So we can now let this be g of t. And how do we prove this using epsilon deltas? We first need to fix epsilon being bigger than 0. And we need to choose some delta. And at this point in time, we probably have no idea what this delta would be. But we will want this delta to be chosen in such a way that when the inputs are constrained, in the ideal situation, the outputs will be constrained by epsilon. Again, if you want to see why this works, you can check it out in the proof in the description box below. So let's go ahead and simplify g of t, and hopefully things work out for us. So we do get the extra t term there, that will be helpful, although the denominator might give us a little bit of trouble. So let's just see what we can get here. So what do we have here? We are going to get mod of g of t to be bounded by, or rather mod of g of t will be equal to modulus of all of that. Let's do it this way. Right? And when we simplify the first term, we actually can pull out the negative sign. And modulus of negative sign just 1. So we're going to get this expression. Now, our goal is to make sure this whole thing is bounded by epsilon. However, this is not entirely obvious how we should go about it, because this term is a little bit troublesome. This term is sort of giving us a little bit of problems here. How do we actually control this term, make sure that it doesn't get too big and whatnot? This is where we will need to do a little bit of, we need to be a little bit careful here. So the trouble of this term happens when t equals to minus 3. Right? We don't want t to be minus 3. We want to make sure that it stays far from minus 3. Okay, so in other words, we want to make sure that t is not equals to minus 3. Because if t is minus 3, then we'll run into problems. Run into many problems. On the other hand, t is located near 0. It's like an error term which we want to get as small as we can. So we can allow this to be the case basically by allowing t to be bigger than minus 3. And at this point in time, you might be wondering, well, should we just take delta to be 3 or whatnot? Okay, let's just play it safe. Let's just play it as safe as we can. And let's make sure we are far away from the minus 3 as much as possible, right? So here's 0, here's minus 3. Let's make sure that t is really as far away from minus 3 as possible. So let's choose minus 1. Right, let's make sure that t is bigger than minus 1. And what this means is that mod of t will be smaller than 1. Right? So we'll make sure that's the case, but let's see what implications this has for us. So by making sure that t is far away from minus 3, aka minus 1, we can... Let's unpack this and see what we get. Let's unpack this and slowly make sense of this. So we're gonna get minus 1 smaller than t less than 1. And this will give us 3 plus t to be smaller than 4 and more than minus 1 plus 3, that's 2. So we're going to get 3 plus t being bigger than 2, which allows 1 over 3 plus t to be smaller than half. Right? The question here, however, tells us that mod of 3 plus t is mod of 3 plus t, right? Well, if 3 plus t is positive, then mod of 3 plus t will be equal to 3 plus t, because the modulus of a positive number is itself, which is bigger than 2, which allows this whole thing to be 1 over 3 plus t to be smaller than half. So let me rewrite all of that. The color for red is not a great choice. Let me use the white color here. This will give us t being smaller than 1 and bigger than negative 1, which tells us that 3 plus t will be smaller than 4 and bigger than 2. But since 2 is bigger than 0, we have that firstly, mod of 3 plus t is equal to 3 plus t, because 3 plus t is positive. Secondly, 1 over 3 plus t, since 3 plus t is lower bounded by 2, 1 over 3 plus t must be upper bounded by a half. So all that's to say, we can bound this guy by a half. And now we can bound the modulus of t by, we can bound this by epsilon, if we were to bound modulus of t by this guy, which means that modulus of t is less than 2 epsilon. So we have these two requirements. The modulus of t being smaller than 1 ensures that the denominator is far from 0 as much as possible. And the bounding by 2 epsilon will make sure that the entire of modulus of g of t will be bounded by 2 epsilon. So we choose delta to be the smaller of the two. And if you are feeling uncomfortable that modulus of t might hit delta, let's just put a half there. That way, no matter what you want, modulus of t will definitely be smaller than 1 and 2 epsilon. And we're done. So it takes a bit more effort here, but we can do it. Okay, let's do the next one. Question 32. We need to calculate this guy. The limit as x approaches 1 of 4 over square root of x plus 15. And we want this to be equal to 1. Well, we want to show that equals to 1. Once again, since x is approaching 1, let's write this as x equals to 1 plus t. And if the entire expression approaches 1, we'll take the entire expression minus 1 approaching 0. That way we can think in terms of error terms. So we will now fix epsilon bigger than 0, and we'll choose delta judiciously such that when the inputs are constrained, ideally the outputs are also constrained by epsilon. So let's do some algebra. The bottom here will become 16 plus t. We can... I'm thinking, should we rationalize the denominator in this context? I think we'll first combine the terms. And then we'll rationalize them at the same time. I think that makes more sense. Oops. Yeah, I think that will make sense. So the numerator will simplify to 4 squared minus 16 plus t. The denominator will simplify to 4 root 16 plus t plus 16 plus t. This could be a problem. The bottom looks really tricky, but let's just see what we can do here. So 4 squared minus 16 plus t, that will simplify to negative t on the top. On the bottom, we are going to get this. Okay, so we can write modulus of gt to be the fraction times modulus of t. We need to make sure that the denominator is non-zero, and the denominator will be 0 when t is close to 16, negative 16, right? So if we have a picture, here's 0, t will be near 0, here's minus 16, we need t to be as far from negative 16 as possible. So the convenient choice in this case is actually just mod of t being bounded by 1. All we need to do now is to try to bound the bottom terms. In fact, there's a little trick that we can even employ here, right? Okay, firstly, by setting modulus of t, okay, so let's just do this one at a time. Let's first simplify this guy. We'll get this expression. And what this tells us is that 4 times the square root of anything plus 16 plus t will be lower bounded by 15. That means that when you take 1 over, it will be upper bounded by 1 over 15 modulus of t. And all we need to do is actually to bound modulus of t by 15 epsilon. However, we actually need to check that the denominator doesn't get destroyed On the one hand, we've shown that the denominator cannot be 0 because we've chosen t to be as far away from minus 16 as possible, and conveniently. And at the same time, we need to make sure that the item in the square root remains non-negative. Thankfully, we do get the condition because the thing inside the square root is 16 plus t. So if we take square root of that, it has to be bigger than or equal to 0. But based on the stipulation of mod t being less than 1, we will get 16 plus t being bigger than 15. So when we take square roots, we don't have a problem. It's all positive. It's all good. So all we need to do to choose delta is the smaller of 1 and 15 epsilon. This sort of combines the reciprocal with the square roots, but the idea is pretty much the same. Alternatively, we could have rationalized at first and then done square roots later, but it's fine. This works too. Alright. Let's go. Let's move on. Let's keep going to question. I have no idea what question we're doing. We did question 32. Right? We did question 32. Alright. Now let's do question 33. This will be the limit as x approaches 3 of 2 over x plus 3 being equal to 1/3. So we need to prove this limit. And how are we going to do that? We're going to use the substitution once again. So we're going to take limit, not as x approaches 3, but as t approaches 0. And since x approaches 3, we will let the substitution be x equals to 3 plus t. We'll take this whole thing minus 1/3. We want this to be equal to 0. Call this g of t. Fix epsilon bigger than 0. Choose delta so that under the constraint of the input, preferably this guy will be constrained by epsilon. Let's algebra our way through. Whoops. Let's do some algebra. It's gonna take some time. Right, so this is g of t. And this tells us the mod of g of t. Okay, we can just write it over here. The modulus of g of t is going to be the fraction times modulus of t. Once again, we want to make sure that t is as far away from the minor awkward. Now, t will be somewhere here, and when t equals to negative of 6, we're going to get a 0 denominator. So we're going to make sure that t is as far away from negative 6 as possible. No problems there. We have mod of t less than 1. This will allow us to get some bounds on t. And since 6 plus t is bigger than 5 is positive, modulus of 6 plus t is equal to 6 plus t. And since 6 plus t is lower bounded by 5, 1 over 6 plus t is upper bounded by 1/5. So let's bound it by 1/5. And we can bound the modulus of t by 30 epsilon. So we need to stipulate these two conditions. And we're going to get delta to be the smaller of these two items. So when you first do the questions, it feels a little bit overwhelming, but it does get better with practice. It actually does. 34. Let's keep going. We're 1/3 of the way there. I am looking forward. This is not bad. We're 1/3 of the way there, and this might take another 4 hours, so Alright. Okay, let's go. I definitely should have played some music. I actually can't hear the music you guys are hearing in the background. I actually can't hear that. But it's fine. I'm just gonna play some music along the way. Hopefully, we'll see what we can do. So here's the example, and we need to solve this using epsilon deltas yet again. So the strategy is to let's make the substitution t approach 0. So in this case, it's x approach 2. We're going to substitute x with 2 plus t. We're going to take this whole thing minus 2 over 5. This should give us 0. So we're going to fix epsilon bigger than 0. Choose delta to be this item here, so that when the inputs are constrained, ideally we have the outputs being constrained by epsilon. So let's go. G of t is this guy. So we can simplify using some algebra. My brain is not working today. Let me not go so quickly. Let's just do that first, right? Okay, great. So that simplifies to minus 2 over 5 times 1 over 5 plus t times t. So that means that the modulus of g of t will be 2 over 5 times 1 over modulus of 5 plus t times t, and modulus of t. And once again, we need to make sure that t is as far away from minus 5 as possible. So we can choose 1 once again. Let's do some algebra. And since 5 plus t is bigger than 4 is positive, the modulus of 5 plus t is equal to 5 plus t, it's a positive number. And since 1 over 5 plus t since 5 plus t is lower bounded by 4, 1 over 5 plus t is upper bounded by 1/4. So we can bound this by that. And we can bound this by epsilon by stipulating that modulus of t is smaller than 10 epsilon. So we have these two conditions. And our choice of delta is as follows. Alright, let's keep going. Question 35. The limit as x approaches minus 6 of x plus 4 over 2 minus x being equal to negative a quarter. We need to, once again, make the substitution. So let's do t approaches 0. Here the substitution is minus 6 plus t, because x approaches minus 6. So minus 6 plus t plus 4 over 2 minus 6 plus t. And we're gonna subtract by the right hand side. This whole thing should give us 0. Fix epsilon bigger than 0. Choose delta such that when mod of t is constrained, the output should be constrained as well. So let's go. this could be a problem. Okay, this looks really painful. Okay, so mod of g of t is 3/4 times 1 over mod of 8 minus t times mod of t. Once again over here, we want to make sure that t is as far away as 8 as possible because we want to make sure that the denominator will never hit 0. So let's choose 1 again because we can. So let's do a little bit of calculations. Since t is between -1 and 1, negative t will also be in between -1 and 1. Okay, you can think about that. So we can add 8 on both sides. That way, 8 minus t is positive, which means that mod of 8 minus t is equal to 8 minus t. And since 8 minus t is lower bounded by 7, 1 over 8 minus t is upper bounded by 1 over 7. Oops. So this simplifies to a rather unwieldy number, but nevertheless still boundable by epsilon. So we can bound this by epsilon because we can set mod of t to be smaller than 28 over 3 epsilon. We need to stipulate these two conditions, which allows us to choose delta to be in between them. So by translating the idea into errors, it really takes a lot less energy to take care of the boundings. It's not mathematically more valid or even less valid in the context of Calculus 1, but it does make our lives significantly easier. So I've been contemplating on this for like a few months now, so it's about time that this be released to the world. Okay, let's go. Problem 36, we need to take the limit as x approaches -1 of this guy. And we need to show that this equals to, I wrote that wrongly, should be 3 minus x, 3 over 2. Yep. So we are gonna, once again, make the substitution. X equals to -1 plus t. We'll subtract by the right hand side. And everything here should be 0. So we're going to fix epsilon bigger than 0, choose delta, so that when this happens, ideally we'll get mod of g of t being upper bounded as well. So let's go, let's try that. Let's do some painful algebra, but at least it's just algebra. Let's just be honest, at least it's just algebra. It's not too much hoop jumping in terms of logical jumps. It's just algebra. It looks painful, but it's just algebra. This guy is a 5 here. The top will simplify to 1 minus t plus 5. The bottom will simplify to 4 minus t. And this will simplify this way. We're gonna multiply it like that. Let me write this minus sign a little bit more clearly, because the probability of careless mistakes is not high, not low. My brain is pretty exhausted and we're not even halfway there yet. We're gonna get there, we're gonna get there, we're gonna get there. Oh wow, this marathon is highly non-trivial. Just butchered that. 2 times 4 minus t. 12 will minus a 2, so that will give us 0. And 3t minus 2t, that's just t. So it's half times 1 over 4 minus t times t. And mod of g of t will be half times 1 over 4 minus t times mod of t. We want t to be as far away from 4 as possible, so we're going to choose mod t smaller than 1, so that we never really, the t stay here, it never really hits the troublesome part of t equals to 4, at which the denominator will be 0. We can do a little bit of algebra here, so t lies between negative 1 and 1, which means that if we take the negation, or if we take the negative of t will still lie in the same region, right? So why is that useful? Because then we can add 4 on both sides. And now we have 4 minus t being positive. So modulus of 4 minus t is equal to 4 minus t. And since 4 minus t is being lower bounded by 3, 1 over 4 minus t is upper bounded by 1 over 3. So we can upper bound this entire expression by 1/2 times 1 over 3 mod of t, and this will be 1 over 6 mod t. We can bound this by epsilon, provided that we allow mod of t to be smaller than 6 epsilon. Since we need to stipulate these two conditions on modulus of t, delta will be the smaller of these two expressions. Alright, let's go to problem 37. Let's keep doing this. We're gonna take the limit as x approaches 5, and I'm not looking forward to it because if we look at the expression, I'm gonna write it over here. Oh no, we are getting both the reciprocal as well as the square root. So you can expect the proofs in this part to be longer. So what is the trick to doing epsilon deltas? The trick is to use a substitution. So let's do it this way. Since x approaches 5, x minus 5 will approach 0. So what do? We're going to let this be represented by t. In a sense, it's like the error term-ish. And we can let x equals to 5 plus t. So instead of thinking of it as x approaching to 5, we can think of it as the error term t approaching to 0. We can now make these substitutions, so x is replaced with 5 plus t. And instead of the expression approaching 7 over 2, it's the same as saying the expression minus 7 over 2 approaching 0. And if you'd like to see why this is true, you can check it out in the proof in the description below. We're going to call this g of t. And what does the epsilon delta proof requires us to do? It requires us to fix any positive epsilon and choose delta to be something so that if the inputs are constrained, we would like, in the best case scenario, the outputs to be also constrained by epsilon. So how do we ensure that's the case? Let's do a little bit of algebra and work some magic out. So let's do this. G of t is 7 over root of 5 plus t minus 1 minus 7 over 2. Let's do some algebra. And we can combine the terms. We can even factor the 7, right? We can actually factor the 7. So that now we're left with 2. So we're left with 2 minus root of 4 plus t. Okay, it takes a little bit of effort, but that's true. And then we can rationalize the denominator. I need a little bit more space here. Let me just create a bit more space. Okay, there we go. 2 plus root of 4 plus t over 2 plus root of 4 plus t. So we are going to get the numerator will simplify to 2 squared minus 4 plus t, because this is a plus b times a minus b. So it's a difference of squares. The bottom is going to be 2 root 4 plus t plus 4 plus t. So it's a little bit convoluted on the bottom. It's a bit crowded there. But when all the dust settles, we're going to get 1 over this fraction. And we're going to get minus t. So we simplify the g of t on the right hand side. This allows us to write there, when this happens, mod of g of t will be 7 over 2 times 1 over modulus of this guy times modulus of the minus t. And modulus of minus t is just modulus of t. So what do we need to do? We need to make sure that the denominator is as far away from 4 as possible. And not just that, what am I saying? We need to make sure that the denominator is as far away from minus 4 as possible. And furthermore, we also need to make sure that it's non-negative. In other words, t must be bigger than minus 4. So on the one hand, here's t. Here's minus 4. We need to make sure it's far away from that as much as possible. Like this. Let's just say 1, because we are really, really sloppy. And we can just use a rough estimate. That should be enough. I don't think that's a big problem. And we need to check that this actually allows 4 plus t to be non-negative. Now, I think it does. But let's just do the calculation. So mod of t, let's stipulate this guy. This will allow t to be in between minus 1 and 1. So when we add 4 on all sides, we'll get this expression. And we'll notice that not only is 4 plus t positive, it's actually bigger than 3. So we will be able to do some bounding later on. That's actually very convenient for our purposes. Okay, so we have now ensured that everything in the denominator is positive. So we can now remove the modular sign. And since the denominator is bigger than or equal to... Okay, let's just do this slowly. So what do we have here? We now have that 2 root 4 plus t plus 4 plus t. Firstly, it's not negative. Secondly, this term has to be non-negative. And we've seen just now that this is lower bounded by 3. So this entire expression is actually lower bounded by 3. And so when we take 1 over, we're going to actually upper bound it by 1 over 3. This will be bounded by 7 over 6 modulus of t, which is bounded by epsilon, given that we allow t to be bounded by 6 over 7 epsilon. We need to stipulate this and this condition. So this is how we are going to choose our delta. Alright, I believe after question 40, we're actually going to do a slightly different type of limit, but I think it's still about the same. So Well, okay, we're gonna take some effort here. Alright, which question were we at? Oh gosh, 37, okay. We're gonna do question 38. Question 38 says this. Okay, this looks really inconvenient because now we have an x cubed on the bottom. And I am not looking forward to this. So firstly, we'll still replace it with t once again. In this case, x equals to 2 plus t. We'll subtract the 2 on both sides. And now we just need to work our magic once again. So this is g of t. We need to fix epsilon bigger than 0, choose delta, so that when we constrain the inputs, we would like the outputs to be constrained as well. Let's do a little bit of algebra. Like this. And we're gonna combine everything and rationalize the denominator as per usual. I might need a little bit more space. Right, so we're gonna do some rationalizing over here. Right, so there's that. Let's simplify. The top, that will be, well, 36 minus all of that. This is a sign that I need to take a short break. So we will take a break after problem 40. Okay, so we have that. On the bottom is gonna be a huge mess actually. Well, this looks very inconvenient. I think I messed this up somehow. Part of me thinks I've messed it up. Yeah, I missed the 2. I actually missed the 2 here. There we go. That looks a lot more like it. So instead of it being 2, it's gonna be 4. Right. We can do some algebra on the inside. This actually looks really painful. Whew! And well, gotta keep going. We gotta keep going. I know the constant terms are gonna cancel out, so that's not a problem. In fact, we can pull out some of the terms here. We have minus 4. We can divide even a 2 on the bottom. So the denominator is gonna be this guy. I think that's correct. Yes, the constant terms will cancel out, so we're left with t times 12 plus 6t plus t squared. I believe if I did the algebra correctly, that should do the trick. If you've spot any errors, please just let me know. I'm more than willing to fix this. This looks horrible. It's like sort of mashing up every single thing that we've ever learned in throughout this entire process so far, right? So what's the trick? Well, there's no trick, it's just really just doing literally whatever we've done before in the past. This guy will be, I know this can simplify to 2, so it'll be 2 times 1 over 3 root of all of that oops, 2 plus t plus that modulus, if you would, times modulus of t times modulus of 12 plus 6t plus t squared. Right away, I can see some little tricks being involved here, but let's just go through it one at a time. The first thing we need to do is to make sure that the denominator is never 0. The denominator is going to be 0 when 2 plus t cubed plus 1 equals to 0, which means that 2 plus t cubed is minus 1, which means that 2 plus t equals to minus 1, which means that t is equal to minus 3. Oh, great. So if t we want to make sure that t equals to minus 3 never happens. But furthermore, we also can make this a little bit more strict. We want to make sure that everything is bigger than minus 3. And the idea is because we want the term in the square root to be non-negative. So here's t. Let's just choose, once again, mod of t to be less than 1. And something quite interesting happens here. Now, firstly, we can write this whole expression as t between 1 and minus 1. So we can add 2 on all sides. This becomes 3. This becomes positive 1. And 2 plus t cubed will be bigger than 1. It will be smaller than 27. We can add 1 on both sides to get bigger than 2 and bigger than 28. So the first thing to know is that the denominator is going to be bigger than or equal to 28. So we can upper bound this guy by 1 over 28 because the square root term has been non-negative. And by stipulating mod of t less than 1, we ensure non-negativity, so we are pretty safe. And at the same time, we notice this modulus of a polynomial here can be decomposed using the triangle inequality. So we can bound this by 12 plus 6 mod t plus mod t squared. And we can now bound all of this in the polynomial term by 1. Because mod of t is bounded above by 1. So let's do the calculations here. This will give us 19 over 14 mod t. And we can get this to be smaller than epsilon by stipulating mod of t less than 14 over 19 epsilon. We need these two stipulations. So our choice of delta, as bizarre as it looks, is actually 1 and 14 over 19 epsilon. Let me see how much battery my phone actually, my pencil actually has. With 5%, okay. We're gonna have to charge our battery, so we'll probably take a short break in just a moment. Okay, so 39. So problem 39 here. We need this limit. And this limit is going to be rewritten as taking t to 0. We're going to write everything. Since x approaches 1, it will be x equals to 1 plus t. and we will subtract by 3 over 2. We want this whole thing to be approaching to 0. So we'll fix epsilon bigger than 0, choose delta, and then we'll need to show that when the inputs are constrained, ideally the outputs will be constrained as well. So let's simplify the outputs by some algebra. I'm just gonna do the algebra directly, okay? So I'm just gonna stare at the thing and I'm gonna try to expand it right away because I am tired. So the 1's and the 2 will cancel out. The 2t and the t will give us 3t. Alright, and we can do a bit more algebra here. It actually is quite clean, I have to admit, so that feels great. I need to multiply everything here by 2 because I'm going to put a 2t on the bottom. This will be 3t. So this will simplify to 6t minus 3t. 2t squared over 2t. And this actually simplifies to, well, this might be a problem. I think I did my algebra wrongly. Things should cancel out if I did this correctly. So I think I forgot to algebra this properly. Give me a moment. I need to debug this. Oh, I actually copied the question wrongly. It's actually x squared minus 1. So, well, that's awkward and embarrassing. Give me a moment. I need to debug all of that. Let's try that again. 2t plus t squared. So let's do some simplifications. On the top, we're gonna get 2 times of 3t plus t squared. On the bottom, it will be that. And I believe things would cancel out, so I think we are good to go. Yeah, this looks a lot more legitimate. Okay, so the 6t's will cancel out. And on the top, we're just left with negative t squared. There we go. In fact, we can even pull out an extra t and cancel them out. So we're left with minus 1 over 2 times 1 over 2 plus t times t. So modulus of g of t is 1/2 times 1 over modulus of 2 plus t times t modulus. And we once again want to make sure that t is as far away from negative 2 as possible. Conveniently, we can choose 1 yet again. So minus 1 less than t less than 1. This means 2 plus t will be bigger than... If we add 2 on all sides, we'll get this inequality. And we'll use the lower bound because it's positive. So 2 plus t is positive. Modulus of 2 plus t equals to 2 plus t. And 1 over 2 plus t must be upper bounded by 1 because 2 plus t is lower bounded by 1. So this whole thing is upper bounded by half times 1 times mod t, which can be bounded by epsilon if we were to stipulate mod of t less than 2 epsilon. So we get these two guys. And that is how we do it. Okay, last one. We are going with this. We're on a roll. Last one, and then we'll take a short break and we'll come back to deal with all of the other terms, all the other questions. Okay, so this itself is a 3-hour run. We'll continue this in a moment. So last one for the day. we're gonna do this. We need to use this, solve this by epsilon delta. So let's prove this. Since x approach 1, we'll use x equals to 1 plus t. So this will be 1 plus t squared minus 1 over 1 plus t squared minus 1 plus t plus 1 minus t. Gosh. We'll minus 2/3 on both sides and show that this has to approach 0. So this thing here is g of t. And we're going to fix epsilon bigger than 0. Choose delta to be something. And we want to show that when the inputs are constrained, ideally the outputs will be constrained by epsilon. So let's hopefully do that. Let's simplify the g of t by algebra. I actually think this is correct. I think I'm correct. I think you can, yeah, I think I'm correct. All right, I think this is correct. Okay, let's just do some preliminary cancellations because we can. There we go. So mod of g of t is 1/3 times 1 over mod of 3 plus t times mod of t. We will need to insist that t is as far away from minus 3 as possible, so we can choose 1. That's not bad. 1 is a pretty good choice here. This will ensure that t is in between 1 and -1. This will make sure that 3 plus t will be bigger than 2, which means that if we take 1 over 3 plus t, it's positive, so it's equal to the modulus. And it's lower bounded by, well, it's upper bounded by half because the denominator is lower bounded by 2. And we're gonna get 1/3 half mod t, 1 over 6 mod t, which will be bounded by epsilon by stipulating mod of t less than 6 epsilon. So choosing this guy and this guy, we will get our answer. So we're gonna take a short break and we will be back. I need to charge this guy and we will be back. Alright, and we are back, and we are gonna continue with the remaining few questions. I anticipate to end all of this hopefully in 4.5 hours. So, let's do question 41. But before we do question 41, we're actually gonna be looking at one-sided limits this time around. So, let's just write out what we mean. we mean this, right? So we say that this guy, I'll just do this in, there we go. We'll say that the one-sided limit from the positive end of the function exists precisely when, for any epsilon bigger than 0, we can find some delta bigger than 0. And the difference in the conditions is that instead of modulus of x minus c, we insist that x minus c is positive. That way x really does lie to the right of c and not just the left. Okay, such that this guy will imply mod of f of x minus L less than epsilon. So that's the definition. And the trick is to use a substitution. So let me explain what do I mean by that. Let's go to the question 41. And we want to solve this limit. We're going to show that this is true via the epsilon-delta definition. The trick here is to observe that, and this is a useful trick just for any epsilon-delta question at all, is to observe that x approaches minus 4 from the positive side means that x plus 4 or x minus negative 4 approaches 0 from the positive side. Let me write it this way, x minus negative 4. Which means that you can let this be t and make the substitution x equals to minus 4 plus t. So that this part over here can be replaced with t. And this thing over here is actually c plus t. So we can rewrite this limit as t going to 0 from the positive direction of, instead of x now, we're going to write it as minus 4 plus t plus 3 to the 2023. And since this expression is expected to approach negative 1, we want this expression subtracted by negative 1 to approach 0. And so we need to show that for any output threshold epsilon, we can find some input threshold delta such that when the inputs are constrained by delta, and we have to be careful this time our inputs are strictly positive, it's not just modulus, it's positive. What we have here is that ideally the outputs are bounded by epsilon. Okay, so let's do algebra and go on the hunt for this delta. So g of t can be simplified to minus 1 plus t to 2023. And we can expand this using the binomial theorem, but I'm going to cheat because it's going to be quite painful to do this fully. So this is going to be minus 1 to the power of 2023 plus all the remaining terms. By the binomial theorem, this is going to be 2023, choose k, from k equals 1 to 2023, of minus 1, 2023 minus k, t to the k, plus 1. Minus 1 to the odd power will be minus 1, so that will cancel out with the 1. And now we're left with this entire expression over here. Okay, so we're going to be left with this summation. I'm going to abbreviate all of these guys by the symbol AK, A sub k. And so what we have here is that modulus of g of t will be bounded by, or rather will be equal to, this sum. We can factor this sum, and in fact, we can still use the triangle inequality, right? We can still use the triangle inequality, and we're going to get this expression. All of the terms will get modulus, if you would. And then, since t is positive, we can replace t modulus of t with just t itself. And what do we have here? We can first pull out a t actually. We can actually factorize a t to get this expression. And we are gonna call this expression, I'm gonna call this expression p of t. And we know that every term there is non-negative, so it has to be non-negative. And we can check that it will actually be positive. We know that if we were to restrict t by 1, so let's just suppose we restrict t by 1. In fact, we know that t has to be positive, so let's just do it that way. Then this expression must be bounded above by t times p of 1. Everything is non-negative, it all works. So we can bound this by epsilon by stipulating t to be bounded above by epsilon over p of 1, which will be well defined. No worries there. So we need these two stipulations, and our choice of delta will simply be the smaller of the two. So you're allowed to sort of abbreviate this long expansion using this notation. It's totally fine. That is what we're gonna do in the next example, because I don't know why I decided to torture myself with these examples. You know, why would we even use epsilon deltas here? Oh boy. Okay, so we need to calculate this limit. We need to prove this by epsilon delta. Since x is approaching 3, we'll make the substitution x equals to 3 plus t. We'll bring the limit over. We want this whole thing to be 0. We'll fix epsilon bigger than 0. We'll choose delta in just a moment. We'll restrict the inputs, which is just positive this time around, because we can do that. We need to constrain the outputs. Ideally, this happens. Let's do some algebra to do a bit of experimentation, and I'm gonna abbreviate just like before, but I'm not gonna detail the abbreviation, okay? Here I'm abbreviating all of the constants. It will be fine. Actually, wait. I think there's a little hack that we can do here. We don't need to subject ourselves to this kind of torture. I think I can hack over here. Okay, I don't think I can hack over here. Well, that's kind of sad, but it is what it is. So it goes to 1 plus summation of 6 plus t to the k, t to the k. So the ones will cancel out. Okay, I think we can actually do a little bit of cheating over here, because this might make things a bit more convenient. So we note that we have to bound this guy, right? Okay, so g of t, this is all positive, so it's actually really nice. It's actually equal to all of this, which is all positive, so we're good to go. And what happens here is that actually we could do a little bit of bounding. We can actually do a bit of bounding here first, just to make things a bit easier. Because if we were to bound this by 1, then the 6 plus t portion will be bounded by 7, right? I mean, that's not very useful in and of itself. But the idea here is, firstly, we can pull out the t. We can pull out one of the t's. And secondly, we can basically treat this whole thing as a polynomial in terms of p. This is a polynomial. Let me do it that way. This is a t times a polynomial in terms of p. And we know that this whole thing will be smaller than t times a polynomial of 1. In fact, we've already made such a stipulation. That's actually pretty convenient. We can bound this by epsilon by setting t less than epsilon over p of 1. So we need t to satisfy these two constraints. It's positive, it's all good. So that settles it. It's not as bad as it seems, even though it does look pretty insane. Okay, let's keep going. I hope to finish this soon, so let's go. Now 43, I'm gonna focus on highlighting the key strategy, and then I will do the manipulation on my own. You guys can try it out if you wish as well. Details in the notes, proofs are in the notes, so that's all of that. We want to prove this limit. Limit as x squared plus 5 approaches, as x approaches 1 of x squared plus 5. That should equal to 6. Right, in terms of t, so x equals to 1 plus t in this context. And we can subtract by 6. We're going to show that this approaches 0. Alright, and in fact, g of t is gonna be t times t plus 2. That's all positive, so feels really good. I like it when it's positive. Let's bound t by 1 because we can do that. That was awkward and embarrassing. Apologies for that. And then we can bound this by epsilon if we were to bound t by epsilon over 3. So we've got this feature and this feature. There we go. So that's how we deal with that. Let's keep going. 44. Here's a square root type of question. Okay, so we need to prove this limit. We are gonna do it this way. Everything's not in 0, so actually it works out very well. But let's just write it in terms of t, since we're so much more used to writing in terms of t. So the substitution here is that x equals to t. I know it doesn't really convey the point, but as you've seen in the general case, it can be quite useful. So let's do this because of familiarity's sake. We'll call this g of t. So we need to fix epsilon bigger than 0. Choose delta to be something, so that when we constrain the inputs, ideally the outputs are constrained by epsilon. So let's go. Let's simplify g of t, which is root of t. Not much to simplify there, let's just be honest. So mod of the g of t, and since square roots are non-negative, it is also equal to root of t. We want this ideally to be less than epsilon, so how can we make this happen? Let's just solve it. In fact, t has to be smaller than epsilon squared. And that's it. We just need this one condition. So that was easier than expected. So let's see what happens when the expressions aren't as easy as we would like them to be. Let's go. Let's find the limit as x approaches minus 2 from the positive side of this expression. So the strategy is to replace x with, well, if x approaches minus 2 from the positive side, that means that x minus minus 2 approaches 0 from the positive side. We can let this be t, and we can make a substitution where x equals to minus 2 plus t. So this means that the limit as t approaches 0, whoops, from the positive side of 4 minus that. We will subtract by the right hand side. In this case it's 0, so it's pretty good. And we want to show that this whole thing equals to 0. So we need to fix epsilon bigger than 0, choose delta, such that when we constrain the inputs, ideally the outputs will be constrained by epsilon, and in this case our inputs don't have any modular signs because we insist that t is positive. Let's go. So g of t is this expression, which we can simplify using some algebra. So we get that g of t will be a non-negative expression. But we need to do a little bit of checks. So the first thing to note is that since t is positive, right, this means that 4 minus t has to be smaller than 4. So negative t is less than 0, so if you add 4 on both sides, you will get that. You can take the square root on both sides. And this right hand side will be simplified by root of 2 times root of t. However, this is an important note for us. We do need to make sure that 4 minus t is non-negative. So we do need to stipulate that 4 minus t is bigger than 0, which means that t has to be smaller than 4. How can we ensure this? Let's just stipulate t is smaller than 1, because we can. It's not because of any reason, it's just because we can. And finally, we want to stipulate this to be smaller than epsilon. What does that mean? It means that 2t less than epsilon, which means that t will be smaller than epsilon squared over 4. Since we need to stipulate 2 conditions, we will set delta to be the smaller of the 2 conditions. And we are good to go. Alright. Let's keep going. That's 45, and now we're doing 46. 46 is a similar problem, I would expect. I'm so tempted to just use the general formula here, but it's okay. Let's just do it one at a time. Similarly, we want to prove this result. So once again, let's use t, and x will be minus 5 plus t. So this will be g of t. We'll fix epsilon bigger than 0, choose delta, such that when we constrain the inputs, ideally we can constrain the outputs. So let's do some algebra. And we need to make sure that 10 minus t is non-negative. to do that, let's just stipulate typo error. And to do that, let's just stipulate t being smaller than 1, because we can. This tells us that mod of g of t is, everything's non-negative, so we can remove the modulus symbol. Because t is positive, negative of t will be negative, so 10 minus t will be smaller than 10, right? And so if you take the square root, you're going to get less than root 10. Right, so that will allow us to bound this by epsilon by setting root of t smaller than epsilon over root 10. Since we have two conditions, okay, sorry, that's not the condition, because we actually have a condition on t, not root t, so t smaller than epsilon squared over 10. Alright, we have two conditions. Let's just stipulate delta to be the smaller of the two. And that's that. We've got a few more to go, and we can keep going. We're gonna end well. 47. Limit as x approaches 3 from the positive side of square root x squared minus 9. We're gonna show that this guy equals to 0. So we'll use the substitution x equals to 3 plus t. And since the right hand side is 0, that is enough. We will fix epsilon to be bigger than 0 and choose delta, so that when we stipulate the inputs, ideally the output will be upper bounded by epsilon. It will be constrained as well. So let's do some algebra here. I believe that's the algebra, so you can check it if you wish. And everything is positive, so we don't have to do those extra stipulations like we did the last time around. It's very nice when everything is positive. So that means, sorry, this should be positive t. So that means mod of g of t is this whole thing. We can even stipulate it to be, well, let's stipulate this t to be smaller than 1, so that we can bound this guy by root of 1 plus 6. And we can bound this by epsilon by stipulating root of t is smaller than epsilon over root 7, which means that t is smaller than epsilon squared over 7. Let's bound by these two guys, and we're good to go. Definitely a lot quicker than the previous round, but it is what it is. Alright, question 48. Let's do 48. We're gonna do a similar question as x approaches 4 from the positive side of x squared minus 16 all square rooted. So we will use the substitution x equals to 4 plus t. This is going to be that. So we will fix epsilon bigger than 0. We'll choose delta, so that when we constrain the inputs, ideally the outputs will be constrained as well. Let's do some algebra on the outputs. Again, I'm cheating because I've done this many times. So what are we gonna get? We're gonna get mod of g of t. Everything is non-negative, so we can remove the square root. We can remove the modulus expression there. Let's bound t by 1 because we can. And let's bound this by epsilon by stipulating that root t is smaller than epsilon over 3, aka t being smaller than epsilon over 9. So we're going to consider these two stipulations and choose our delta to be the smaller of these two guys. I just realized I'm really on the right. Okay, good. There's a much better angle. Now, 49, let's go. Keep going, 49. We need to calculate this limit. And we're actually looking at these kind of reciprocal limits. So the trick here is to observe that x approaches 2 plus means that x minus 2 approaches 0 from the positive side. We can let this be t, and we can use the substitution x equals to 2 plus t. That usually makes the calculations a lot cleaner. So this is the same as saying the limit as t approaches 0, but instead of x we're using 2 plus t. And since the expression approaches 1, in an ideal world the expression minus 1 approaches 0. So let's call this g of t. And what does the epsilon delta definition require of us? It requires of us to fix epsilon bigger than 0 and choose delta to be some expression, we'll find out later, such that when we stipulate the inputs, and this time the inputs are are actually positive inputs, right? They have to be positive because we are going from the right side. Ideally, we would like the outputs to be bounded by epsilon. That's the best case scenario. So let's check it out. Let's do some algebra. And we are going to get modulus of g of t being equal to modulus of t over 1 plus t. But however, we also notice that t is positive, so the numerator is positive, the denominator is positive, and we can actually remove the modulus symbols. And I might even write it this way because we can now do a little bit of bounding. So we'll notice that t is positive, which means that 1 plus t is lower bounded by 1, and 1 over 1 plus t is upper bounded by 1. 1 over 1 is 1, which means that we can bound this by t. How do we bound this by epsilon? Well, we just set delta to be equal to epsilon. So that when t is smaller than delta, then t is by definition smaller than epsilon. And we're done! Great! And you can see that this sort of really cleans up a lot of the epsilon delta and all of that. It makes things a lot easier. I'm just saying, it makes a lot of sense. Okay, so let's do question 50. Alright, we are officially halfway there! That's encouraging! We need to find this limit. Or rather, we need to prove this limit using epsilon deltas. And since we are approaching 3, the substitution will be x equals to 3 plus t. And we can subtract the 2 on both sides. So that this whole expression will approach 0. In the best case scenario, of course. So fix epsilon bigger than 0. Choose delta to be some value such that when we constrain the inputs, ideally we get a constraint on the outputs. So let's constrain the let's check out what g of t is. we're gonna get that expression. So modulus of g of t is gonna be the modulus of 2 minus 2t over modulus of 5 plus t. Since t is positive, the modulus of negative 2t is gonna be just 2t. And since t is positive, 5 plus t is positive, we can just keep that as 5 plus t. In fact, we're gonna even put a t over here because we notice that the denominator is lower bounded by 5, so it is up. So 1 over the denominator is upper bounded by 1 over 5. So let me write it this way, so it's a little bit more obvious to see that the denominator being lower bounded by 5 means that 1 over 5 plus t is upper bounded by 1 over 5. Alright. And this will simplify to 2/5 t, which is less than epsilon, if we stipulate t to be smaller than 5 over 2 epsilon. And what's 5 over 2 epsilon in this context? Well, that's just our delta. Or at least that's what we're going to choose our delta so that all things work out. This is very convenient. Okay. Woo! We are at the halfway mark and we are ready to continue, but I might take a short break later because my Apple Pencil needs some charging. But let's go! Okay, so we've looked at right-hand limits, but we can do the same thing with left-hand limits, right? Because we can say that we get a left-hand limit precisely when, for any epsilon bigger than 0, there exists some delta bigger than 0, such that now instead of x minus c, we're now saying c minus x. C minus x must be positive, which means that x is smaller than c, aka from the left side of c. This will allow the outputs to be controlled by epsilon. And once again, the trick is literally almost the same. So we're just gonna roll with it. So we need to calculate the limit of this guy equals to 1 from the left hand side. And what that means is, well, we first want to convert this. Now, since we're looking at it from the left hand side, the substitution is not going to be 2 plus t. We normally would substitute x equals to 2 plus t. This time, however, we're going to take x equals to 2 minus t. So the idea is that x is 2 minus some, right? X equals to c minus t. So that the idea is x is 2 minus some deviation from the 2. Also to say that we can still take limit as t approaches 0 from the positive side. But now we're going to use, let me write it this way. If x approaches 2 from the minus end, that means x minus 2 approaches 0 from the minus side. But that means that 2 minus x approaches 0 from the positive side because of the negations, which means this is what we can make to be our t, which means that x can be used, we can use the substitution x equals to 2 minus t. And that's what we're going to do here. So there isn't in fact this kind of confusion. We can just work with t as a positive error term. And once again, we subtract by the output, because if the expression approaches 1, then the expression approaching 1, then the expression subtracted by 1 should approach 0. The proof is in the notes, it's in the description, in the video link, so you can go and check that out if you wish. We will let this be g of t. And what does the epsilon delta definition require of us? We need to fix epsilon bigger than 0 and choose a delta so that when the input lies in between these is constrained by delta, and because of our formulation, we are still insisting that t is a positive number. Again, we like positive numbers, so feels good. Ideally, when this happens, we want the output to be bounded by epsilon. And now we're on a hunt for delta, which requires a bit of algebra. And this is our expression. And we might need to do a little bit of work here because there is a bit of negative signs to take care of, as you can see. So mod of g of t will be mod of t squared. In fact, we can factorize, right? Let's try that. Mod of t times t minus 2. We can factor this using, well, we can factor this and we can simplify this way. And we can upper bound t minus 2 using the triangle inequality. It's been a while since you've seen this, right? Now, in our formulation, t is positive, so we can remove the modular signs because it's positive, it works. Let's bound t by 1 because we can. And bound 3t by epsilon by stipulating that t be smaller than epsilon over 3. Since we need these two conditions, and we need t to be smaller than delta, we'll simply choose delta to be the smaller of these two conditions. And we are good to go. So that's basically the difference. It's basically your right side limit because we're letting t approach 0 as long as we use the correct substitution. And we're going to see a little bit of that in the future questions as well. Let's try the next one. So this one will be limit as x approach 3 from the negative side of x squared minus 3x plus 6. This should equal to 6. So let's make the transformation. Since we are approaching 3 from the negative side, we're going to use the substitution. Okay, since x is going to 3 from the negative side, we're going to use the substitution x equals to 3 minus t. And once again, we'll take this whole expression minus the right hand side. This should give us 0. So we'll fix epsilon bigger than 0. And we'll choose delta to be some number that will work out for us in a moment. We'll stipulate the inputs to be in between this region. And hopefully the outputs will also be contained by epsilon. Let's do some algebra. The 6's will cancel out. The 9's will cancel out, interestingly enough. And we can factor a t. So what this tells us is that mod of g of t will be mod of t times mod of t minus 3, which we can upper bound using the triangle inequality. And since t is positive, we can remove this symbol. Let's bound t by 1, again, because we can. And let's bound this whole thing by epsilon. So we choose the smaller of these stipulations. And that's our answer. Great. Definitely starting to get a feel for what's going on. Let's do this. Limit as x approach 4 from negative side of the square root of x. So what do we have here? Okay, so once again, since we're going to 4 from the negative side, we'll make the substitution x equals to 4 minus t. By putting the substitution there, it sort of helps us keep track what we are doing. So this will become 4 minus t. And since the 2 is on the right side, let's just subtract it out. We get that. So we'll fix epsilon bigger than 0 and choose delta to mean something. Let's stipulate the inputs, and hopefully the outputs will work. So let's simplify the outputs using some algebra. This calls back the technique of rationalization, just to get rid of the square roots. This will simplify to a squared minus b squared. On the top, and we're going to get minus t over root of 4 minus t plus 2. So modulus of g of t will be modulus of all of that. So the minus sign, modulus of negative t, will be just positive t. The bottom is not negative, in fact it's positive, so we can leave it as it is. Once again, we need to make sure that everything in the bottom works out well. So let's let's ensure that this guy has to be bigger than or equal to 0. So t has to be smaller than or equal to 4. Let's choose a easier stipulation, t smaller than 1. This will make everything legitimate. And now we notice that the denominator is lower bounded by 2, so the entire expression will be upper bounded because, okay, let me write this way. Since the denominator is lower bounded by 2, the reciprocal is bounded above by half. Right, we can bound this by epsilon by stipulating t smaller than 2 epsilon. Again, we've already checked that everything on the bottom will check itself out, so we don't have to worry about that. We choose these two stipulations. That's it. Okay, let's keep going. So we're gonna do the limit as x approaches 100 from the negative side of 101 minus x equals to 1. Since we're approaching 100 from the negative side, we're going to make the substitution x equals to 100 minus x. X equals to 100 minus t. So t will still go this way. There we go. And in fact, we want to write it this way, right? We want the entire expression to go to 0. This is g of t. So we need to fix epsilon bigger than 0 and choose delta so that when we stipulate the inputs, we will get this conclusion, ideally. So let's work our way through. Now I believe I can actually do this. Okay, this is my claim. This is my claim. And the reason why is because everything is positive. So this works, and then we can get root of t. So let me just prove this claim really quickly. The claim says that root of 1 plus root of t squared is equal to 1 plus 2 root t plus t, which is bigger than or equal to 1 plus t whenever t is non-negative. So we need to make sure that everything's non-negative, and then when we take square roots on both sides, we get the result. So we can do this. We're allowed to use these little tricks, if you would, so that mod of g of t is bounded above by root of t. And once it's bounded above by root of t, we are good to go. We just need to bound this by epsilon. And how do we do that? Root of t bounded by epsilon, so t is bounded by epsilon squared. So we just need to choose delta to be epsilon squared. These shortcuts work, and in fact, I believe that this statement is true in general, so we can use this in our toolkit. So if this is always true, we can always bound this by mod A plus mod B. This is called the triangle inequality. For square roots, we can do something similar, assuming both terms are non-negative. So we can do that if we make the assumption that they're non-negative. In this case, it works, so we're good to go. And that's why I love non-negativity. Non-negativity makes life really easy in general. Okay, now we have that in our toolkit. I might be using that a lot more. Okay, so here's our claim, or rather we need to prove this limit. So we will make the substitution x equals to 2 minus t. And this guy is g of t. So we'll fix epsilon bigger than 0, choose delta, so that when we stipulate the inputs, ideally, the outputs will also be well controlled. So let's simplify the outputs using some algebra. And unfortunately, because of the negative sign, it sort of destroys my plans to do that trick. So we have to be careful. Let's just allow this expression to be non-negative. And to guarantee that, let's just stipulate t being smaller than 1. And even then, it's quite difficult to use. So unless it's really obvious that I can do it, I usually will avoid it. So let's just first make this stipulation so that mod of g of t can be written as root of t root of 4 minus t. And we know that t is positive, which means that 4 minus t has to be smaller than 4. You're taking 4 and you're subtracting a positive number, so it's smaller than 4. And when you take the square root, you can bound the square root term by 2. And you can bound this by epsilon by stipulating that root t is smaller than epsilon over 2. Or in other words, t being smaller than epsilon squared over 4. We have 2 stipulations. And so we will do just that. And that's our answer. And we can move on. Okay, next question is going to be similar. 56 is similar. So I might go a little bit faster, right? So we're approaching 6 from the negative side. Our substitution is going to be 6 minus t. So we'll let this be g. And write down our desired stipulations. Let's do some algebra. And I'm gonna fast track this because I'll notice that when you stipulate this guy to be positive, no negative, you can just use t being smaller than 1. And what happens when t is positive? 12 minus t will be smaller than 12. You can bound it by root 12. You can upper bound it by root 12. So let's fast check the whole process. And let's bound this by root of t, root 12. We can bound this by epsilon by stipulating root t smaller than epsilon over root 12. T smaller than epsilon squared over 12. We have two stipulations. I should have done one of them in white instead of green, but it is what it is. And we are good to go. Okay, we are making good progress. We're making good progress. Next question. We'll take the limit as x approaches minus 3 from the negative side. And that would give us root of x squared minus 9 equals to 0. So from the negative side, what we need to do is to substitute x equals to minus 3 minus t. Okay, so it's a bit of a mouthful, but that is our substitution. We'll let this be g. Fix epsilon bigger than 0. Choose delta in a certain manner. Stipulate the inputs. And we hope that the outputs will be controlled by epsilon. Let's do some algebra. And this time around, well, we can do some factoring. Since everything is positive, we're gonna actually just do it this way. Right? That's a little hack over there. Okay. Although it doesn't really matter in this context, but it's fine. Okay, so we have modulus of g of t. Everything is positive, so it all works out. Okay. Let's stipulate t to be smaller than 1, because we can. And then we can stipulate, well, this simplifies to 1. So we can now stipulate t, well, we can make this smaller than epsilon if we were to stipulate root of t be smaller than epsilon over 1 plus root 6. And when we square on both sides, we get something horrible. Yeah, that looks pretty disgusting. I think splitting it up wasn't the best idea ever. I could have left it inside. But either case, with these two stipulations, we are good to go. I think in this quiz, I should have just remained inside the square root. That might have been a better idea. Okay, let's keep going. So now we know I'm gonna just stay in this where I'm gonna stay where it's more convenient. If I want to find this limit, since we are approaching 7 from the negative side, we'll use the substitution x equals to 7, x equals to minus 7 minus t. Man, my brain is slowing down. Please do not do marathons if you guys can afford it. Please revise consistently rather than speed run through an entire... How many hours is this worth? 4 hours so far and counting. This guy is gonna be 0, and we need to make this g of t. So fix epsilon bigger than 0, choose delta, such that by constraining the inputs, the outputs will be constrained, ideally, this way. And g of t, we can do some algebra. I wrote wrongly, it should be 7 minus t. This is a sign that it's time to take a short break, but it's all good. Alright. I'm gonna fast check the algebra. And this time I'm not gonna split because we split the last time and didn't really work out for us. So, oops. This guy is gonna be this expression. Whoops. Let's stipulate t being smaller than 1 because we can. And we can make this less than epsilon by stipulating root t smaller than epsilon over root 15, which is given by t being smaller than epsilon squared over 15. So we can take the smaller of these two items. Oops. And there we have it. Okay, we have a few more examples to go. And these next ones don't look really friendly, so this is gonna be somewhat fun. We're gonna get a quadratic expression, and this looks really long. 5 plus 4x minus x squared equals to 0. So once again, we're approaching 5 from the negative side, so that means x will be 5 minus t. That's our substitution. We're gonna get 5 plus 4, 5 minus t, minus 5 minus t all squared. We want this to be 0. Fix epsilon bigger than 0. Choose delta such that when we stipulate the inputs, the outputs are going to be, hopefully, whoops, what am I doing? Smaller than epsilon. Algebra time. You can see my handwriting progressively getting worse. Ah! Okay, let's go. Okay, we have that. And we'll get 5, 20, 40. There we go. The constants, if I'm right, will cancel out. We're gonna get 6t minus t squared. And here we have to be pretty careful, because we need to make sure that 6 minus t is positive, right? Otherwise the square root function is not even defined. So the idea here being that here's 6, well, here's 0, and here's 6. We need to make sure that that t is nowhere near 6. So let's just choose t being smaller than 1. We can do that. That way 6 minus t will be positive. On the other hand, since t is bigger than 0, 6 minus t is smaller than 6. So when we square root on both sides, we will get square root of 6 minus t being smaller than root 6. So this is less than root of t root of 6, which will be less than epsilon. If we were to stipulate that, root of t is smaller than epsilon over root of 6, which is obtained by t being smaller than epsilon over 6. Let's choose these two stipulations. And we are good to go. Alright, we're hitting a 60. We're hitting 60. That's a good sign. We are hitting 60 and that feels great. Okay, 60, let's go. Wow, what's that? Was it that simple? Wow, it was really that simple. Because the problem looked really complicated, but it turned out to be a simple calculation when the algebra checks out. So use algebra. Use the trick. It's really good. It's a really good trick. Never knew this existed, but it feels good. So we need this guy. Since the stipulation, or rather we're approaching 1 from the negative side, so we're going to take x equals to 1 minus t. And we want this to be equal to 0. So we'll fix epsilon bigger than 0. We'll choose delta so that when the inputs hold, ideally the outputs will be constrained as well. So let's do algebra. And on the inside, we are getting something a bit strange. I have to admit, this is definitely probably one of the more bizarre types of questions, but we can still do it. It's not a problem. We can still do it. I might maybe even pull a little trick here. Okay, so we have the... Did I make an error? Yes, I made an error. This should be a minus sign. Oh gosh, it's so irritating. Minus 2 plus 4t minus t squared. Okay. I don't think that really changes the question that much. Or it changes the challenge that much. We're gonna get 9 minus t squared and minus 3. So I could try to do that little trick that I did just now. I don't have to, because we can just use rationalizing of the expression. So let's rationalize. Okay, so let's just do rationalizing. On the top, we're gonna get a difference of squares. So this will simplify to negative of t times t plus 1 over this thing. Part of me thinks there's a problem with this proof, but I'm gonna have to take a look here. I think we're good to go. It is just one of those long questions, but it's doable. It's entirely doable. Okay, let's take a look at this. So we have modulus of g of t is equal to, since t is positive, we will have modulus of g of t being modulus of everything there. The fraction itself without the negative sign is positive. So if the modulus of the negative is just the fraction itself. And let's first stipulate that the denominator, the item inside the square root, ought to be positive. And you can check that t less than 1 does the job. This will allow 9 minus t plus t squared to be positive. I'll let you guys check that out on your own. Right? So that will allow us to upper bound this fraction, because the denominator is lower bounded by 3, the entire term will be upper bounded by 1 over 3. We can use the same bound of t being smaller than 1 to get 2/3 t. And this guy will be smaller than epsilon when t is bounded by 3 over 2 epsilon. And we will get that. And that is that's how we do it here, right? In fact, the working actually looks pretty clean, all things considered. The work, most of it is the algebra. Alright, that's question 60! Yes! Yeah! Let's do something. I don't know if this is more fun or not, but you know, we're getting there. We took 1 hour to complete 20 questions, and that's not bad. I have to admit, that's not bad. I'm actually meeting a friend later. Caris, if you're watching, hi! Hope you're enjoying this. I'm meeting Caris later at 7:45, and the travel time is not trivial. So this could be a problem. Okay. Now, we also want to look at the limits at infinity. So we say that the limit x goes to infinity of f of x equals to L. Now, instead of the condition being there exists a delta, now we want x to be as large as possible. It's not x being constrained to some constraint, but x being as large as possible. So we need to show that for any epsilon bigger than 0, there does not exist a delta, but there exists an m. And it's not x being constrained by a delta, it's actually x being greater, bigger, insanely crazier than m, such that that would imply that the outputs are constrained. So this definition might be a little bit unfamiliar to us when we see it for the first time. And it was a little bit for me. But I was thinking about it, and I was thinking of how can we sort of... Is there a hack to this? Is there a simpler way to do this? Turns out there is. And I've left the details in the proof in the notes, so you can go check that out if you wish. But here is the trick. So we're going to look at the next question. We need to calculate this limit. We need to show that this guy equals to 2. Now, the trick is, again, a substitution. This time, the substitution isn't as obvious. So what substitution are we going to use? In my notes, the idea is this. Since x is getting really, really large and positively large, 1 over x is becoming small, but positively small. So the idea here is, could I use this substitution t to replace 1 over x so that x can be substituted by 1 over t. So the idea is that instead of thinking of x going to infinity, we think of 1 over t, where t is going to 0 from the positive side. This allows us to take all of our ideas from one-sided limits into this version. So that's the idea, that's the key trick, and that is what I'm going to do here. So instead of thinking in terms of x approaching infinity, I'm going to replace it with t approaching 0, but now I'm going to replace every single instance of x with 1 over t. And once again, whatever is approaching is 2. So whatever it is minus the thing it's approaching, ideally should equal to 0. To see that this actually works, I've left the proof in the notes in the description below. You can go check that out if you wish. So, ironically, to prove this, we're gonna just prove the right side, the one-sided limit, like what we did before. So, fix epsilon bigger than 0. We'll choose delta to be some term such that when the t's are constrained, mod of g of t will still be constrained, ideally. So we reduce the entire problem to something we're familiar with, and we just need to algebra our way through. And therefore we have mod of g of t equals to 2t over 1 plus t. Since t is positive, we can upper bound this guy by 2t because, well, 1 over 1 plus t is bounded above by 1. Sorry, scratch that. 1 plus t is lower bounded by 1, so 1 plus 1 over t. that 1 over 1 plus t is upper bounded by 1. So we can bound this by 2t. And therefore we can just simply bound this by epsilon. Since t, we can stipulate it to be smaller than epsilon over 2. And that's how we deal with limits at infinity. We just convert it using a substitution. And if you're wondering whether I'm just pulling a sleight of hand here, you can check out the document, you can look at the proof. It works. It just works. So this is a really powerful way of doing limits. Let's do this one. And for this limit, since we are letting x to infinity, we're going to use the substitution x equals to 1 over t. Since we're going to positive infinity, t will be going to 0 plus. Okay, bring the 3 over 2 over and let this whole thing approach 0. So we'll fix epsilon bigger than 0, choose delta, so that when we constrain the inputs, ideally the outputs are being constrained as well. Let's algebra our way through, and we notice that actually things work out really nicely for us. Okay, I think that's what it works, but now we actually have to be a lot more careful than we used to be, right? Because now the denominator is not as friendly. So let's just do all of that. Alright, let's just do that. Mod of gt is going to be 15 over 2 times 1 over mod of 2 minus 5t times t is positive, so we can remove the modular sign. Now we need to be a bit more careful because we need to make sure that t is as far away from the 0 point as possible. And this time we can't use 1. Because if we think about it, 2 minus 5t being equal to 0 means that t is equal to 2 over 5. So it's a lot, the room for, the wiggle room here is a lot smaller this time around. We have to be very careful. So t is here, we'll put 0 here, and 2 over 5 is here. Let's choose a number that's smaller than 2 over 5. There are a few options. I think we can go with, let's go with 1 over 10. You could go with 1 over 5 actually, but let's just do 1 over 10. And that will allow us to conclude that, okay, so t being smaller than 1 over 10, what does that tell us? It means that 5t will be smaller than half, which means that negative 5t will be bigger than minus half. 2 minus 5t will be bigger than 2 minus half, which is 3 over 2. And therefore, modulus of 2 minus 5t is positive. It will equal to 2 minus 5t bigger than 3 over 2. And we take 1 over, we can bound it by 2/3. So it still can be done. We just need to be careful, but it still can be done. 2/3 t. Now we can bound this by epsilon by stipulating t being bounded by epsilon over 5. We need these two conditions, and this time t less than 1 is a bit too broad for us, but it's fine. So we need that. Alright, okay, that was a bit more interesting. Okay, so 63. Let's prove now that this guy happens. So since x goes to infinity, we're gonna use a substitution x equals to 1 over t. We will subtract by the limit that we hope to show. I'm going to show that this guy is 0. Alright, let's do some algebra. And just like before, we have to take care of the 2t minus 1 business. It's not as straightforward as we hoped. So we want to make sure that t is as far away from the 0 point as possible. In this case, 2t minus 1 is 0 when t is a half. Right? So this time we will choose maybe, let's just choose a quarter. So let's stipulate t being smaller than a quarter. What good does this do for us? 2t will be smaller than a half, which means that 2t minus 1 will be smaller than negative half. I know this looks a bit concerning. Right, so I know this looks a bit concerning. You're like, whoa, what's going on here? Okay, don't worry, don't panic. This looks concerning until you realize that this whole expression 2t minus 1 is negative. So if you were to flip everything, you get this expression. And in fact, mod of 2t minus 1 is going to be equal to 1 minus 2t, because 2t minus 1 itself is negative. So it's going to be the negation. It's going to be the negative version of that. So let me write it down this way. This is going to be minus of this guy, because 2t minus 1 will be negative. So no worries, don't panic, it's all good. And what we are getting here is modulus of 2t minus 1 being bounded this way. And using the lower bound, we can take the reciprocals to bound it above by 2. So it is still doable. Just need a little bit more care and concern. And we can bound this as per usual. So we're going to get this bound, right? That will be our bound. And that's it. And we're good to go. So yeah, it takes a bit of effort, but you know, it's fine. It's just something we get used to. The point is we can sort of use the substitution to solve the infinite limit using a finite limit. Let's solve 64. So x goes to infinity. We have a clear substitution here. We use x equals to 1 over t. This is our g. And we hope that our outcomes will be bounded by epsilon. So g of t. Let's do some algebra. So this is our expression. Interestingly enough, the fraction itself is positive. So when we take modulus of g of t, by algebra, this is actually 7t over 3t plus 2. And I'm actually going to write it in... I'm going to split up each of the terms. Since t is positive, we don't have to worry about lower bounding and all of that. It will never hit the 0 point. It's totally fine. And since the denominator is lower bounded by 2, the reciprocal is upper bounded by a half. And finally, we can bound this by epsilon by setting t to be less than 2 over 7 epsilon. And we are good to go. So sometimes we get lucky and sometimes we are not as lucky, but in either case, we can still fix the problem. It's totally fine. Alright, 65, and we are making good progress. We are getting there. We are getting there. We are getting there. We are getting there. Let's calculate this guy. We claim that this guy actually goes to 0. So once again, the substitution will be 1 over t, right? X equals to 1 over t. And we want to show that this guy eventually can get as small as possible. We want to bound this guy. So let's do some algebra. As you can see, probably we'll need to do a bit of work to make sure that everything is not too badly behaved. Part of me wants to rationalize, and yet part of me is thinking, I think we can work with this. I think we can work with this, and the reason why is this. Alright, now of course, we need to make sure that everything here is not badly behaved, and unfortunately, 1 minus 5t will be 0, means t will be equal to 1 over 5. So we still have to avoid the 1 over 5 mark. So let's just choose 1 over 10. So let's stipulate this guy. Let's just write out g first. Let me just write that out. Everything should be positive, right? So by stipulating that, we are good to go. But I want to go... Okay, I think this should work. So we have a little bit of wiggle room between the 0 and the 1 over 5. And the idea... Okay, let's just bound things and see what we get. 5t, oops, 5t will be upper bounded by a half. Negative 5t will be lower bounded by negative half. We add 1 on both sides. We get this guy. We can square root throughout. And what do we get? We're gonna get 1 over root of 1 minus 5t being upper bounded by root 2. Because, well, this guy is 1 over root 2. So if you 1 over that, you can get root 2. So it still works. Everything still works. And we can avoid the 0 denominator. We are good to go. There we go. So we can stipulate this to be less than epsilon if we allow root t to be smaller than epsilon over 8 root 2, which means t will be smaller than epsilon squared over 128, because that's 8 squared times 2, 64 times 2, 128. So we can stipulate these two things. And that is how we do it. Alright, it's not too bad, it's not too bad. Of course, it takes a little bit of thought to make sure that we don't break any rules, but as a whole, it's doable. Let's keep going. 66. So we're letting x go to infinity again, which means I'm going to use the x equals to 1 over t substitution. And we want to try to control this guy. We want to hopefully bound this guy by epsilon. As you can see, it feels a lot more straightforward in that sense in terms of the strategy. We don't have to worry too much on what to do. We just have to do it. Oops. Okay, so we have that. Once again, the denominator is not so friendly to us. We actually need to be very careful here. We need to make sure that everything works out. Now, the denominator will be 0 when t is 1 over 5. So we cannot use 1 over 5. Let's choose 1 over 10. And let's just make sure that everything in the denominator, it's well behaved. So let's do 5t, 1 minus 5t. Let's cube it. And let's take the reciprocal. So we're still good to go because this whole expression, g of t, is equal to 8 times 1 over 1 minus 5t cubed. And this is positive. When we stipulate t being smaller than 1 over 10, this will still be positive. We are still good to go. So this whole expression has to be smaller than 8 times t cubed, which is 64 t cubed. And we can stipulate this to be smaller than epsilon if we allow for t cubed to be smaller than epsilon over 64. And t to be the cube root of that. And cube roots will preserve inequality signs, so we don't have to worry about that. So these are our two stipulations. And we are good to go. Whew. Alright. 67. I have a feeling that later at about 80 we might need to take a break because this guy might be running out of juice. I'm not too sure, but we'll see when it happens. So we'll do it this way. Alright, x goes to positive infinity. The substitution will be x equals to 1 over t. We want this term to approach 0, so we'll fix epsilon bigger than 0. Choose delta. That's a badly drawn line. It's okay. Okay, suppose this happens, then this will happen. Let's do some algebra. So this will simplify to the algebra here is slightly complicated, but we will get there. It's not a big problem. And what do we have here? The 6's will cancel out. Usually when the constants cancel out, we're good to go. Usually, because then everything else, in some sense, can be controlled. Okay. Oh, try that again. All right. So 1 over, I've almost forgot that. So mod of g of t will be t times mod of 1 minus 6t. We actually don't know whether this is positive or negative, so we need to be careful there. We're gonna try to make it positive eventually, alright? And then we have this expression as well. So what we need to do is we need to be careful, because on the one hand, we want to make this 1 minus 6t business be positive, so we can remove some stuff. You know what? It's okay. For that, let's just use the triangle inequality. That's fine. But the bottom one, the denominator, is a bit more of a concern, right? Because this will equal to 0 when t is plus minus root 3 and root 5. So in other words, here's 0 and here's root 3 over root 5. We need to make sure that t lies really contained. So let's just choose, let's let this be root 3 over 2 root 5, because we can cheat. That's the classic way of cheating. And we should be able to obtain good results. So let's take t squared. You will get 3 over 20. I believe that's correct. So 5t squared will be 3 over 4. It's a little bit, let me redraw that. And 5t squared minus 3 will be 3 over 4 minus 3. I can't do mental sums. Minus 9 over 4. Now this is bigger than 0, so this will be bigger than minus 3. Again, it looks like things are really tough, but thankfully everything is actually negative, so we can actually just flip the symbols. And this will be our modulus of 5t squared minus 3. This will be upper bounded by 3 and lower bounded by 9 over 4. So the fraction, this fraction, will be upper bounded by 4 over 9. Because the 1 over will be upper bounded by the 1 over lower bound. So all to say, we can upper bound this firstly by using the triangle inequality. And secondly, we can bound this by 4 over 9 by our analysis. I guess that's why you call this module analysis. Now you could use this stipulation, but it's really unwieldy, so I'm not going to do that. I'm just going to stipulate something extra. T being smaller than 1. Totally fine. We can take the minimum of everything. Everything's going to work out. So this will be allow us to stipulate, or rather this will help us bound the 1 plus 6t with 7. Alright. And we can bound this by epsilon by choosing, t smaller than 9 epsilon over 28. The amount of reverse engineering here is crazy. So, we actually have 3 stipulations this time. It's possible, but again, these all work out. You're taking t to be the smallest of all of them. Totally fine. And that is how we do it. So the trick is sort of to see what you need to use to bound some stuff, right? Okay. 68. Where are we at now? 20 minus 9x plus 8x squared over 7 minus 2x squared equals to negative 4. And let's make the substitution x equals to 1 over t. Let's call this whole thing g. Fix epsilon bigger than 0, choose delta bigger than 0, choose delta, which will be bigger than 0, so that stipulating the inputs, we can control the outputs, ideally. Let's algebra the g of t, and this looks horrible, but it is fundamentally a problem in algebra. I would use a computer to help me do this, but it's fine. Let's just do it manually. Oh wow, that's a lot of t-squares. We have to be careful again, right? Because now there's some denominator business. Kind of sucks, but it is what it is. And just like before, we have to do some careful bounding. I think there are a few other ways to go about this, but you know what? Let's just fine, whatever. Let's just stipulate t, because we need to make sure that, right? Well, let's just do it here. Here's root 2 over root 7. Here's minus root 2 over root 7. Apologies. Let's just stipulate t to be smaller than that. So we just take the divided by 2 version. So t stipulated to be root 2 over 2 root 7. This will allow us to have t squared to be 1 over 14. And 7t squared to be smaller than half. Which means that 7t squared is smaller than negative 3 over 2, but it is bigger than negative 2. So everything's still well contained and it all still works. Which means that if we were to flip everything, firstly we get a modular sign. Secondly, everything will be positive. So now let's just write this all out. And finally, since we get a lower bound on modulus of 7t squared minus 2, we get an upper bound on its reciprocal. So this guy will be upper bounded by 2 over 3. Right? And let me justify that a little bit more clearly. So when you take 1 over, when you take reciprocals on all sides, we can upper bound it by 2 over 3. So this guy is bounded by 2 over 3. For the linear term, once again, we can, I'm going to put modular sign here, this is actually a modular sign. We can bound it using the triangle inequality. And let's stipulate t smaller than 1 here, so that we get a very convenient bound. This number is divisible. This number, I think it's 38. 57 divided by 3, it's 19. 19 times 2 is 38. So this is 38t. If that's the case, so we need to stipulate these 3 things throughout our argument here. 1 root 2 over 2 root 7 epsilon over 38. And that's it. That's our choice of delta. Obviously, it's way more involved, but it still works. And at the end of the day, even though the algebra is what's messy, the calculations still work. Alright. The question whose number shall not be named. I know the internet is screams at this number, but let's not go there. Okay, we need to show that this guy equals to 0. So once again, we will make the substitution t approaches 0 from the positive side. So this will be making the replacement x equals to 1 over t. Fix epsilon bigger than 0, choose delta to satisfy some conditions such that when we when we stipulate the inputs, the outputs will be stipulated as well, or be controlled. So let's do some algebra. This simplifies to 3t over 1 plus 2t. Now this is really nice actually, because this is just 3 over 1 plus 2t times t. And because t is positive, this whole thing will be bounded above by, firstly, the modulus of gt is just this thing. And secondly, when you bound it, it can be just bounded by 3. So it's really nice. But let's do it one step at a time. Modulus of g of t is 3 over 1 plus 2t times t, because everything here is positive, so we can remove the modulus symbol. And since t is positive, right, 1 plus 2t is bigger than 1, so 1 over 1 plus 2t is smaller than 1, and when you multiply 3 on both sides, you can bound this by 3, get 3t, really nice. And this will be smaller than epsilon. I have to say though, it is a nice proof. Where are we again? Yes, t being smaller than epsilon over 3. I'm sorry, my attention span is really decaying exponentially at this point in time. Okay, problem 70. It's basically the same one as just now, but now it's a minus sign. But I can imagine some trouble, because now minus signs, we need to do a bit more fancy footwork. Replace x with 1 over t. And this is our function that we want to control. Fix epsilon bigger than 0, choose delta, so that when we stipulate the inputs, ideally the outputs, are stipulated. That will be the dream. Let's go. It's 4:34. Whew! Okay, let's do this. Algebra. I think it's the same idea here. And now we need to be careful, because now we don't always get a very nice denominator. Now we must actually take care of the 1 over 2t minus 1. So what we're gonna do in this context is, once again, here's t, 0, 2t minus 1 equals to 0 when t equals to half. So we need to make sure t stays far away from half. So let's make sure that happens by choosing a quarter. So let's stipulate t to be smaller than a quarter, so that when we take 2t, it's smaller than a half, and 2t minus 1 will be smaller than a negative of a half, but bigger than minus 1, because remember t is positive in our context here. So 1 minus 2t will be in between 1 and half. This is actually our modulus of 2t minus 1. So why do we care about modulus of 2t minus 1? Because we're taking the modulus of gt equals to 3 times 1 over, let me angle this differently, we're taking 1 over modulus of 2t minus 1 times t. So we need to make sure that we can do the lower bound, and then we can upper bound the 1 over as follows. So we can bound this by 3 times 2 times t, which can be bounded by 6, well, which equals to 6t, and can be bounded by epsilon by setting t smaller than epsilon over 6. So we need to make sure that t is smaller than epsilon over 6 and smaller than a quarter. So we take the smaller of the two. And that's question 70. Okay, we are getting there. We are getting there. We are getting there. Feels good. It's 436. Okay. Oops. Now we've looked at the case when we've taken x all the way to positive infinity, but likewise we can take x all the way to negative infinity. So once again, we can define this to mean for any epsilon bigger than 0, there's this sum m bigger than 0. Okay, I know some of you are wondering what's going on here. Such that when x is smaller than any negative number, negative of m, if m is positive, then negative of m must be negative. So whenever x is really large negative, the outputs will be bounded. And you might be wondering once again, do I have a little trick up my sleeve over here? The answer is yes. I always have a trick up my sleeve. So let's consider this problem. Okay. So the trick up my sleeve works this way, right? So firstly, x approaches negative infinity. So that actually tells us that negative of x approaches positive infinity. Right? That actually tells us negative x is positive infinity. But we know how to deal with positive infinity. We use the substitution 1 over the expression. So 1 over this expression has to approach 0 from the positive side, which means I'm gonna let this be t, which means that I'm going to use the substitution x equals to minus 1 over t. Again, instead of thinking of it as x going to negative infinity, I'm taking the negative of 1 over t going to 0 from the positive side. The proof is in the notes. It works, it checks out. You can go check it out in the description box below. So the trick up my sleeve here is that I'm going to use the substitution. Because we're going x to negative infinity, we're going to use the substitution x equals to minus 1 over t, so that, and here's the beautiful part, when we take t, we're actually taking t to 0, still from the positive side. We're transforming everything we know into positives, which makes life easier. Math people are the laziest people on earth. And that's why we come up with ideas like this. So we replace x with negative 1 over t. And show that this thing will be controlled. Again, to see that the proof works, you can go check out the notes. It's all there. So we fix epsilon, we choose delta, such that when we restrict the inputs again, t being positive. T is still positive. In all of our discussions here, t will be positive, and that's the beautiful part of this argument. Never have to worry about negative symbols. It's amazing. So when this guy happens, ideally the output will be bounded by epsilon. So let's go! My sanity is dipping with every second I'm doing this. Let's do some algebra. Again. And we're gonna write everything in this manner. So I'm gonna write it. Okay, this looks wrong. I'm so sorry. This is actually wrong. This will be negative. Oh, this is negative 2t. This will be t minus 1. So we're gonna get 2t over 1 minus t. Okay, I'm gonna write it this way, and the reason why will become a bit more evident later on. Again, because t is positive, no worries there. So now we need to control this, and sadly 1 doesn't work because what makes 1 minus t equals to 0? T equals to 1. So we actually must avoid 1. How do we avoid 1? Oops. We need to avoid 1. How do we avoid 1? Let's just choose a half. So let's stipulate t being smaller than a half. That will make our lives a little bit more easily. Yeah, a little bit easier. Can't English today either. Negative t is going to be bigger than minus half. So 1 minus t is going to be bigger than 1 over... Well, what am I doing? 1 minus half, which is 1 over 2. And therefore, when we take 1 over 1 minus t, it's going to be smaller than 2, because we're doing reciprocal flipping. And since it's positive, it's equal to the modulus. So it works out very nicely for us. So this whole thing is bounded, is bounded by 2. And we can stipulate this to be smaller than epsilon by choosing t smaller than epsilon over 4. And that is how we do it. So yes, we still have to take care of the denominators, but with enough practice, it's not that big of a deal. Alright, 72, and we are pretty far. We're almost 75% of the way there. That's actually pretty cool. So we're gonna take a limit as x approaches negative infinity. Alright, this whole segment is just negative infinity of this expression. So since we're using negative infinity, the substitution will be x equals to negative 1 over t. Make sure everything is, 0. So this is g of t. Woo! Why did I say f of t? Sorry. G of t. Okay, so we need to find the input so that when that's restricted, the outputs will be restricted as well. Let's do some algebra. And now let's do some careful observations. 1 minus 9t is 0 would mean that t is 1 over 9. So we want to avoid 1 over 9. So let's choose 1 over 18. And since 1 minus 9t is positive, that equals the modulus. So, what do we have here? Mod of g of t is 27 times 1 over modulus of 1 minus 9t times t, because t is positive. This whole fraction is bounded by 2! Alright! Whoops. And we can bound this guy by epsilon over 54. So therefore, we can stipulate these two conditions. Whoops. And we are good to go. So this reciprocal hack is pretty good. But of course, if you want me to show the proofs for these problems without the reciprocal hack, feel free to let me know in the comment section below. Or rather the substitution hack. Now, we'll let, what am I saying? We need to calculate this limit. And since we're going to negative infinity, the substitution is going to be negative 1 over t. So this guy will become g of t. We can fix epsilon bigger than 0, choose delta, so that when we stipulate the inputs, ideally the outputs will be stipulated as well. I've literally said that phrase 73 times. The reason why it's pretty important because that is the goal of this question. If you don't output the g of t, then what are you supposed to do? You don't really know. So we have this expression. I think there is a theorem that talks about how you can actually control an expression of this form. But it's fine, we don't need it. We can just do usual bounding things. So we want to make sure t is not near 2, so we can choose 1. 1 is a pretty good choice this time around. So we can stipulate 1. So 1 over 2 minus t is upper bounded by 1. Since 2 minus t is positive, it must equal to the modulus. And we care about modulus because mod of g of t is going to be t, 1 over mod of 2 minus t times t, which is bounded above by 1 times t, which is bounded above by epsilon if we choose delta to be equal to epsilon. That's very convenient. Okay. Alright. Let's go. Let's keep going. This is 73, 74. This is... My hands are cramping up from this. It's... Whoo! This is what we're looking for, and we need to, since it's a minus infinity situation, we're going to substitute negative 1 over t. Whoops. And we need this to be... My brain just stopped working for a moment. Okay. So, once again, I feel like throughout this stream, my brain has been having a few short circuit moments. Okay, enough nonsense. Let's just solve it. We're almost there. We're gonna hit problem 80, and I might be able to be on time with my meeting with Karis. So let's go. Fix epsilon bigger than 0. Okay, where are we? Okay, here we go. When we restrict the inputs, we need the outputs to be restricted. So what does that mean? It means that, okay, let's do some algebra. And over here, we need to take care of the denominator because we get zeros when t is plus or minus 2. So let's stipulate t to be smaller than 1 because, well, let's just visualize again. There we go. Pretty safe. In fact, we have to avoid minus 2 as well. Kind of strange, but yeah. Anyway, I'm going to stipulate t to be smaller than 1. So t squared will be, well, if t is positive, then t squared will also be stipulated this way. We have to be careful with squares. Then minus t squared and 4 minus t squared. So 1 over 4 minus t squared will be, since 4 minus t squared is lower bounded by 3, 1 over that is upper bounded by 1 over 3. And then since 4 minus t squared is positive, it will equal to the modulus. So therefore, whoops. There we go. Modulus of g of t will be 2t squared, that's positive, nothing to worry there, times 1 over 1 modulus of 1, 4 minus t squared. We know this thing is upper bounded by 1/3, so we can go ahead to do that bound over there. Whoops. And we can make this upper bounded by epsilon by choosing t squared to be, you know what? I'm gonna do it this way. T squared smaller than epsilon. The reason why, okay, you might be wondering, wait a minute, what sorcery am I doing here? Well, t squared being less than epsilon is given by t being smaller than, smaller than epsilon. Okay, what magic am I conjuring here? I'm taking 2/3. But this guy will definitely be less than epsilon. So therefore, we're gonna get that. Okay, we're gonna take a break at problem 80 and then we're gonna finish it up, okay? We're gonna take a break at problem 80 and we'll finish it all up. So, we might take a break at 75 and then we'll finish everything else. Okay, so, what we're doing, we're gonna stipulate this guy and this guy. Yes, these are our two stipulations. And we are good to go. We're gonna finish 75 and we're gonna go for one last break before we finish up this 100 epsilon delta stream, and it's like 5 hours now. This is gonna be fun. Okay, let's just finish up 75 because it's about there. Actually, we could have taken a break at 70, but that's fine. Okay, let's go. Once again, x approaches negative infinity, so x is gonna be minus 1 over t. Let's do our setup as per usual. And let's do some algebra. and we need to avoid minus 1 and 1, so let's just choose half. And we can make the bounds as follows. Let's keep going. So modulus of g of t is gonna be 2 times t squared times 1 over modulus of 1 minus t squared. And we know that the fraction can be upper bounded by 4 over 3. And let's bound this by 1 over 16. Okay, no, never mind, it's okay. Let's it's fine. Let's just bound it by epsilon and just do the usual approach. There we go. So that's our two stipulations. And we will be back. I need to charge the pencil one more time, and we will be back to finish up the remaining 25 questions. And we are back on our last part of this speed run, if you would, of the epsilon delta proofs. 100 epsilon delta proofs. We're gonna finish it this time around. Hopefully there's enough juice in this guy for that. Now, give me a moment here. So, let's do example question 76. And whoops. Here's the limit. It looks horrible. But the proof strategy is basically the same. So we're going to use a substitution. X equals to -1/t. And of course, we will be dealing with one last situation later on in the stream, so stay tuned for that. There will be questions 81 onwards. Okay. Let's do some substitution. Subtracted by 6. And we are ready to go. So we will fix epsilon bigger than 0 and choose delta so that when we stipulate the inputs, what will happen to the outputs? Well, the outputs would ideally go to 0. So let's do some algebra. The numerator looks horrible. That's t plus 60t, that's 61t. T squared plus 6t squared, that's 6... Yeah, that's 7t squared. Well, the bottom looks absolutely atrocious. Part of me wants to just hack it with this part, but no. We need to do it. So, this expression will be equal to 0. Yes, we actually need to complete the square. Oh boy. Who knew? And we need to solve this guy. So t is 5 minus or plus root of 24. We have to be careful, because 5 minus root 24 is pretty close to 0. It's actually pretty close, so we have to be careful. Now 5 plus root 24 is way over yonder, so we don't have to worry about that. So we have to choose a number that's smaller than 5 root 24. I'm just gonna choose this guy. 5 minus root 24 over 2! Alright! That works, and it's positive, so it still works. So we're gonna stipulate this guy. Again, the whole idea here is to avoid doing 0 denominators, but surprisingly, this also helps us deal with, what do you call that? This also helps us make sense of the bounds on the 1 over terms. So this looks horrible. Well, this absolutely, this looks disgusting, really disgusting. Let's do it this way. Let's do it this way. Well, this is awkward and embarrassing. We need to... Okay, you know what? Let's undo that. Let's do it this way. There we go. Okay. I think we are on the right track here. Yes. Right. There we go. Part of me thinks there's a more efficient way than this. I think I made a typo error. This was actually not the correct calculation. Darn it. Well. Yeah, this calculation is wrong. I'm so sorry. This is not the calculation. Ah! Okay. Okay, fine. Whatever. I don't give a... Okay, never mind. Woo! This looks more like it. 26 minus 5 plus t all squared equals to 0. So, oops. Well, 5 plus t equals to plus minus root of 26. T equals to minus 5 plus or minus root of 26. I think now we are pretty safe because minus 5 minus root 26 is really small. It's negative, so we don't have to care. And negative 5 plus root... Oh, negative 5 plus root 26 is still pretty close to 0. So we're going to choose... we're not going to choose that. We're going to choose this number. Minus 5... Or rather, minus 5 plus root 26 all over 2. We're going to do that. So, t, well, we got a 5 plus t, right? So 5 plus t will be, oh, this is bigger than 0. Will be smaller than 5 plus root 26 over 2. So we don't have to worry about 0 denominators, right? And we can square everything. That works out very nicely for us even. I'm just gonna put it this way, squared. I'm quite sure we don't really need this because we're gonna take 1/overs later, most likely. Or do we? Well, that's awkward and embarrassing. Actually, I do need to know what's this number. I actually do need to know that number. Okay, I think okay, let's just do that. There might be a chance I actually need it. So we can take negative signs on everything. Oh, I don't think I need it. Alright, great. So, let's just do it this way. I'm just gonna call this box squared. Okay, we don't actually have to care about what this is. So, great. So, minus 5 plus t all squared would be bigger than negative 25 and smaller than negative box squared. We can put a 26 there. And when we take 1 over that, we get it bounded above by 1. So this is actually our 1 over 1 minus 10t minus t squared. And we can put a modular sign as well. So all of that is to say, we're gonna go. It's long, tiring, irritating, but we're gonna go. So let's go. Modulus of g of t is 61t plus 7t squared. We could actually factor the t over here, so let's do that. Divided by all of that, and we know that we can actually write it this way. And this fraction is bounded above by 1. So let's stipulate t being bounded above by 1 as well. So we know t has to be bounded above by this guy, and that the thing on the right over there is positive, so it works out. It has to be stipulated by this, so that we can get 61 plus 7, which is 68t. And we can stipulate this to be less than epsilon when t is less than epsilon over 68. There we go. So that took a little bit longer than expected, but it works. There we go. Alright. I think the next few, we may or may not encounter that. I'd rather not encounter it, of course, but it might happen. Who knows? Okay, so let's do the next one. That was 76. So we're gonna go to 77. This is our expression. we need to show that this guy will eventually equal to 2/5. Negative infinity means minus 1 over t. So let's show that this whole thing will basically vanish. Alright, let's do some algebra. And we need to make sure that the 5 minus t is non-zero. Whoops. Try that again. So we make sure that t is not equal to 5. To do that, we simply stipulate t smaller than 1. Pretty good, because once again, 0, 5, let's just choose 1. Choose a smaller number. We'll be good to go. And we can do some bounding. And since 5 minus t is positive, it is equal to its modulus. And that gives us mod of g of t equals to t, because that's positive, 2 over 5 plus 3t. That will be positive, right? Everything there is positive. And 1 over modulus of 5 minus t. So we know that the modulus, the fraction term, will be bounded above by 1/4. And we can try to bound the second term by 1 as well. So that we can get a simple expression. This will be 17 over 20, I think. Which will be bounded by epsilon when we stipulate, well, when we stipulate this guy. So we stipulate these two conditions. And we are good to go. That's 77. Let's move on to question 78. The limit as x goes to infinity, negative infinity, apologies, of 5x squared minus 3 divided by 7x squared minus 31x equals to 5 over 7. So replace x with negative 1 over t. And show that this guy is able to go to 0. So let's go. Let's do some more algebra. And this time the denominator is non-zero because t is positive, so it will never be 0. In fact, it can be bounded above. Well, the denominator is bounded below by 7. So therefore the fraction is bounded above by 1 over 7. Now because there's a 7 over there, I'm gonna actually stipulate t to be smaller than 7 because I want to get rid of the denominator. I don't like those weird denominators, it's not fun. And we are gonna get, well, 158 over 7, which can be bounded above by epsilon by stipulating that t is lesser than 7 over 158 epsilon. Now I believe part of me thinks you can actually, simplify the number. Part of me not sure. I don't know. I don't care. Let's just use these guys as our delta. Okay, that's it. I mean, it doesn't really matter. As long as we can do it, it works. That's the most important part. 79. We're gonna deal with this limit. Replace x with negative 1 over t. And we want to show that this equals to 0. So fix epsilon bigger than 0, choose delta, so that when we stipulate the inputs, we can stipulate the output. We can control the outputs. So let's go with that. Let's do some algebra. So modulus of g of t is gonna be 6t cubed. Surprisingly not too bad for us. And all we need to do is to stipulate that to make this guy less than epsilon, we just need to make sure that t cubed is less than 1 over 6 epsilon. In other words, t is smaller than the cube root of 1 over 6 epsilon. We can basically make that our delta. Of course, it's not a nice number. Of course, it's pretty ugly. It works. It just works. It's pretty good. Alright. Alright. Let's go to question 80. Okay. Now instead of the cube, we're looking at the cube root. And I have a good feeling that we shouldn't have a problem here. So once again, replace x with negative 1 over t. And we want to show that this guy will vanish. So fix epsilon bigger than 0. Choose delta. So that you stipulate the inputs, the outputs get controlled as well. Let's algebra this. Now we can take cube root of a negative number, right? That is actually allowed. Right? With square of negative number, you gotta go into the complex numbers, but when it comes to cube root, you're good to go. And the modulus of g of t is 6 cube root t. We want to stipulate this to be less than epsilon. So let's choose cube root of t less than 1 over 6 epsilon. T will be less than 1 over 216 epsilon. And that's question 80. Alright, we are 80% done. We are left with 20 questions and I want to go for my dinner. So, whew, let's do this. Now, we have one more type of limit to deal with, and that is the case when the limit itself is infinite. What we have done is the case when we're asking when x goes to infinity, what happens to the function? Now we're actually asking the question, what happens to the function as x approaches a value? Does that function blow up or not? So we will say that, and we can write it this way. This expression blows up to positive infinity precisely when, no matter which number you pick, you can always find a delta such that when you stipulate the inputs, and in this case we're using the right hand inputs just for simplicity, the outputs will always exceed any finite positive number. So no matter which number you choose, I can always exceed it. I can always exceed that. Once again, it can be a bit unwieldy to use this definition. So, do I have a hack for this? I think everyone knows that yes, I do have a hack for this. So, let's look at the example here. Okay, so let's look at this example. Now, this example tells us that the expression will approach positive infinity. Now, we've seen how to transform this kind of things before, right? We've actually seen that to let an expression approach infinity is a positive infinity is the same as letting that same expression approach 0 from the positive side. So in fact, of course, we can still use our t transformation. That still remains. So in this case, x approaches 3 from the positive side, we'll use 3 plus t. But now we can go one step further and say that it goes to positive infinity precisely when the reciprocal goes to 0 from the positive side. Now maybe I can unpack this here. What we mean by this statement is that for any epsilon bigger than 0, there exists a delta bigger than 0, such that if you stipulate the inputs, then the output is not just controlled by epsilon, but it is also positive. Okay, so in that sense, it's a lot like, okay, maybe I'll use g of t here. Let's not use f of t, it's very confusing. G of t. We mean that the output is not just within a certain distance, but it is actually positive and bounded above by epsilon. Okay, so that's what we mean. So it's analogous to the right hand limit definition. But the beautiful thing is, firstly, this is legitimate. You can check it out in the proof in the description box below. And secondly, I never have to worry about infinite limits. I just need to check the reciprocal. And I'm good to go. So, let's do it. So let's try to ascertain this expression. This is g of t. So in fact, we need to fix epsilon bigger than 0. Choose delta. So that when we stipulate t to still be positive, ideally, g of t is now not just modulus of g of t is less than epsilon, but g of t is between epsilon and bigger than 0. So there is a subtlety over there. So let's check. Let's see if we can get this property going for us. We will get 3 plus t minus 3, which is t. And, well, we can actually, we know that t is definitely positive. So, we know that t is definitely positive. So, since t is positive, g of t will be positive. So, this is good to go. And in order to make this less than epsilon, right? So, in order to make this less than epsilon, so we just need to stipulate that t is smaller than epsilon. So we choose delta to be epsilon. And that's it. That's how you prove that the function has an infinite limit. If the reciprocal has a limit of 0 from the positive side. So we're gonna see this in action many times, and it's gonna be pretty useful. So let's do this question. Let's approach 30/7 from the positive side. So what does this mean? It means that, firstly, we can write this as t, approaching from t, so we replace everything with 30/7 plus t. And secondly, we're taking the reciprocal. Okay, so what we might do, I think I'll do it this way, just to make things a bit more useful, is that this is the same as showing that the reciprocal approaches 0 from the positive side, and we can deal with one-sided limits with relative ease. Since x approaches 30/7 from the positive side, we're going to make the substitution x equals to 30/7 plus t. I think we can see that this is going to be pretty well controlled. So let's go. Fix epsilon bigger than 0, choose delta, so that when we stipulate the inputs, ideally, this is our g of t, we would like the outputs to be positive and smaller than epsilon. So there is a little bit of trickiness involved there. Let's do some algebra. I believe this is just 7t. I think it's just 7t. Yeah, not 70, but 7 times of t. Well, so since t is positive, means that g of t is 7 of t is positive, so we're going to go there. And to bound this above by epsilon, we'll just let t be smaller than epsilon/7. And that's it. And you can actually check that the proof still works. The proof will work in this modified setting. It really works. You can go check it out. It's in the description box below. So 83. Let's do 83. We're going to find this limit. And once again, we can rewrite this as showing that the reciprocal goes to 0 from the positive side. And finally, since x approaches 5 on the positive side, we'll use a substitution x equals to 5 plus t. So let's do that. Here is our g of t. Let's prepare our setup as usual. So let's see what happens. Okay, so g of t, let's do some algebra. So g of t is this guy. It is t squared. And t squared is going to be t squared is definitely going to be positive when t is positive. So therefore we definitely can get this property. And we need to stipulate this to be less than epsilon. So we'll choose t squared less than epsilon, which means that t is smaller than root of epsilon. That's it. I feel like these problems are okay. I'm getting a bit confident here, you know. We are making very good progress. So here's our expression. Once again, to show that the limit goes to positive, to show that the function goes to positive infinity, the reciprocal goes to 0 from the positive side. And since x goes to minus 7 from the positive side, we'll replace x with minus 7 plus t. So this is our new g. I will have to say that I think it's pretty obvious that it's going to work, but it's okay. Let's just use the epsilon delta way. What are we going to get? Oh, darn it. Let's go. We want this to happen, so let's check. We get t to the 4th, which is definitely going to be 0 when t is bigger than 0. So this works. And to make it less than epsilon, let's just choose t to be the 4th root of epsilon. The positive 4th root. You get the point. Yeah. Alright! Let's go! Okay, this is a little tricky. This one's a little bit, how do I sort of make sense of this one? So, I think it's pretty safe to say from high school that as you let x approach to infinity, x squared is gonna go to infinity and it's gonna go really quickly. However, we want to try to prove this rigorously. So how do we do it? Surprisingly, it is the same idea. Firstly, to show that the expression goes to infinity, you need to show that the reciprocal goes to 0 from the positive side, still positive side. And secondly, since we're taking x to infinity, we're going to use the substitution t, apologies, x equals to 1 over t. We can chain these techniques together. If you look at the proofs and you chain them properly, it's gonna work. So we're about to finish this. Let's go! Alright. I am going insane right now. Okay. So here's our expression. Fix epsilon bigger than 0. Choose delta. So that when we stipulate the inputs, I'm feeling it. We would like g of t to be positive and smaller than epsilon. So g of t is going to be 1 over t squared, which is 1 over t squared, which is t squared. And well, t squared is going to be positive when x is positive, so we are good to go over there. And how do you stipulate it to be less than epsilon? We will just choose t to be smaller than root of epsilon. And that's it! Alright! Okay, this is very convenient. Problem 86. Let's do this. Okay, so it's a slightly more complicated expression now. Okay, so we need to show that this guy goes to infinity. Is equivalent to show that the reciprocal goes to 0. From the positive side. And since we're taking x to infinity, we're going to make the substitution x equals to 1 over t. Okay, this is our g. Now it's not as obvious as before, but it's fine. We want our outputs to lie inside 0 and epsilon. So let's just do a little bit of algebra and work our magic. So let's do that. Let's multiply everything by t to the 4th. On top, we're going to get t to the 4th. On the bottom, we're going to get 1 minus 5t squared. Okay, so we need to be careful this time around. we can make the whole thing positive as long as we make the 1 minus 5t squared there positive, right? So 1 minus 5t squared, we make it, in fact, not just positive. We know that this guy will be 0 when t is, for the positive case, 1 over root 5. So let's just consider, let's stipulate t to be smaller than 1 over 2 root 5, in other words, half of 1 over root 5. And that way, we don't have to worry too much. So t squared will be 1 over 20. 5t squared will be 1 over 4. Minus 5t squared will be bigger than negative 1/4. We get to put 1s there, so we get 3/4. And I'm gonna lower bound this by a half, just for convenience. So 1 over 1 minus 5t squared, it's positive. We know it's positive, so we don't have to worry about modular signs, and we also get the g of t property, so this whole thing will be positive. And it will be upper bounded by 2. So 0 will be, whoops, we get this. Whoops, try that again. 1 over 1 minus 5t squared. This fraction will be upper bounded by 2. And let's upper bound it by 16 so that I can take 4th roots very easily. Okay, great. And this guy will be upper bounded by epsilon, which means that I need to simply solve this guy, this expression. There we go. So we have stipulated this condition and this condition. And there we go. There we go. Alright, we are making good progress here. We can chain our different techniques together. That's totally allowed. So don't worry about that. So we're gonna take, we want to show that the square root function approaches infinity. So this means that the reciprocal approaches 0 from the positive side, and therefore if I replace x with 1 over t, this should work. So let's check. This is g, fix epsilon bigger than 0, choose delta when t is bounded by these guys. Then g of t, which is 1 over root of 1 over t, is gonna be root of t. And we know that this is non-negative. In fact, when t is positive, this guy is gonna be positive. So 0 is smaller than root of t, well, smaller than g of t, which is equal to root of t. And this guy, root of t, can be bounded by epsilon simply by choosing by squaring on both sides. So you get t smaller than epsilon squared. Okay, great. A few more to go. 88. This is exciting. This is actually exciting. The limit of this guy goes to infinity. Now, of course, you could use some form of comparison test and all of that, but let's not do that. Let's we're gonna use purely by epsilon deltas because I don't know why I subjected myself to this torture. Anyway, so it goes to infinity if its reciprocal approaches 0 from the positive side, and x goes to infinity means we can substitute t equals to 0 from the positive side. Substitute x equals to 1 over t. This here is our g of t. So fix epsilon bigger than 0, choose delta, so that when the inputs are constrained, we want this to be constrained as well. I believe g of t would definitely be positive. We don't have to worry about that. But let's just do the math and see what happens. Okay. Yeah, g of t is definitely going to be positive because t is non-zero. So 2 times non-zero plus, well, the denominator is going to be positive, so g of t is definitely going to be positive. Let's just see what it evaluates to. And let's recall that if t is positive, then 2 plus 7t will be lower bounded by 2, taking square roots, and then we can take reciprocals. We will definitely get the a bound over there as well. So we are going to get root t over root 2 plus 7t, but this guy is going to be upper bounded by root t over root 2. We can bound this by epsilon simply by choosing root t smaller than root 2 epsilon, right? And then t smaller than 2 epsilon squared. Great. That's that. Alright. And it's not even 6. Alright, let's go. 89. Let's do it this way. Limit as x approaches 1 from the positive side. We're gonna do this gun. So once again, this thing approaches infinity precisely when the reciprocal approaches 0. And since we're taking x approaches 1 from the positive side, we replace x with 1 plus t. So we'll do this. And we'll do this. And we'll do this. Alright, and this guy has to be positive because of t being bigger than 0. This has to be positive. And we can make this smaller than epsilon by stipulating that root t be smaller than 3 epsilon, which means that t is smaller than 9 epsilon squared. And that's that. Alright. Let's go! I love the fact that the limits are zeros and I don't have to worry too much about making sure there's non-zero elements, and feels good, feels good. This hack feels really, actually it feels really useful. So we have this expression. Let's show that we will get it. To show that the function approaches positive infinity, we need to show that the reciprocal approaches 0 from the positive side, and this means that since x approaches 6 from the positive side, we replace x with 6 plus t. So fix epsilon bigger than 0, choose delta when 0 less than t less than delta. We want this to happen. So let's do some algebra. Now the algebra should be pretty obvious. It's actually 1 over 6 root t, and t is being positive, so g of t will definitely be positive. And to make this bigger than, smaller than epsilon, all we need to do is to stipulate root t smaller than 6 epsilon, t smaller than 36 epsilon squared. Woo! We have 10 questions to go. I should be able to make it for my dinner. Okay, alright. Now, 91. Okay, so what we have here, we've dealt with the case when a function goes to positive infinity. For negative infinity, it's basically isomorphic. So we say, and we're gonna just illustrate using the right hand limit here, although you've seen that we could easily tweak the requirements, that this guy will be negative infinity, and here's the formal definition. If for any positive m, I know positive m, we will settle that later, there exists a delta positive such that when the input is constrained by delta, the output will be smaller than minus m. In other words, no matter how negative your number is, I can always make it more negative than what you give me. In that sense, it goes to negative infinity. Once again, this is not the most useful definition. It can be useful, by the way, but when it comes to solve the calculations, it might not be so useful. How do we resolve this? Well, let's make the observation here that this guy simply means negative of f of x being bigger than m. So actually, what we have here is we could even rephrase this limit as, we could rephrase this as the negative of the function is infinity. But if the negative of the function is infinity, then from what we've seen in the previous video, if you haven't watched it, you can go and click somewhere on the screen of the previous part of the stream. For a function to go to positive infinity, its reciprocal must go to 0 from the positive side. In fact, this is you could even jump from here to here as a formulation. If you want to see if this trick works, you can check it out in the proofs. It's all there in the description box below. You can go check out the proofs. Knock yourselves out. It works. And so, these are all the different types of the limits that we're ever going to encounter in calculus. And in our last 10 questions, we're going to finish this up. Let's go! So, question 91. Here's the expression, and we're going to show that it approaches negative infinity. Yep. So how do we show this? Again, you could think of it as the negative, right? Firstly, the negative of this function must approach positive infinity, which means that its reciprocal must approach 0 from the positive side. But finally, what does that mean? Since x approaches minus 3 from the positive side, we can still replace it with t. We are allowed to replace it with t. X equals to minus 3 plus t. So we need to show that this guy is 0 from the positive side. So let's do it. So basically we rephrase all our problems into the basic epsilon-delta formulation. That's really the best way to go. What do we like? We would like g of t to be positive and bigger than epsilon. So let's do some algebra. So g of t will give us this expression, and we need to check that it will be positive. So we need to make sure that 2 minus t is not 0. So in other words, t is not equal to 2. Let's stipulate, since we want to make sure that t is not bigger than 2, we just choose 1. So t is smaller than 1, which means that negative t is bigger than negative 1. And therefore, t is positive and 2 minus t is positive. So therefore, g of t would definitely be positive. Furthermore, we get a bound, because 2 minus t is bigger than 1. 1 over 2 minus t is smaller than 1. So this guy is going to be t times this, which we can bound by t times 1, which we can bound by epsilon, well, smaller than epsilon, via t smaller than epsilon. So we need to use these two choices and take the smaller of the two. And we're done. It looks so complicated, but the algebra really checks out the calculation. So, fun stuff. Okay. 92. X goes to minus, well, what am I doing? Minus 3 from the negative side. It's a bit of a mouthful, but it is what it is. Of x minus 1 over x plus 3 is negative infinity. Okay, lots of conversions here. This is like the most conversion-inducing question. Firstly, we're going to keep the minus 3 minus there, just, right? Although I think you could also convert it to a plus, but it's fine. Let's not go there. It's as complicated as it gets. Since we're looking at negative infinity, we meet, firstly, the expression itself, the negative, must go to positive infinity, and therefore the reciprocal should go to positive, 0 from the positive side. And finally, since x is approaching minus 3 from the negative side, we are gonna use the substitution minus 3 minus t, because negative side. So, there we go. So this is our g. Let's prepare our setup. And we want g of t to be between 0 and epsilon. Let the algebra do its thing. And this is where I'm actually really thankful for algebra. Why did I do that? Goodness. There we go. I'm very glad that we have algebra. Okay, so this is where we sort of run into a problem, because we expected g of t to be positive. I think that I might have made an error in the question. So give me a moment to consider this reality. Yeah, actually, the question here, actually, the reality is that actually it's a positive infinity. Yeah, so let's just do this modified question over here. So there we go. There we go. And now it's pretty clear that it's gonna work. So there is that. Yeah, okay. So where are we? Yeah, so let's do this. So 0 is definitely smaller than g of t. And since t is positive, the fraction will be bounded by 1/4. We can bound this by epsilon via t smaller than 4 epsilon. Right, so there's a question bug on my end, but here's the correct question. So here we go. We need to prove this result. How do we prove this result? Once again, to show that a result goes to negative infinity, the negative of the expression will go to positive infinity, so its reciprocal must go to 0 from the positive side. Finally, since x approaches 5 from the negative side, t will approach 0 from the positive side. What am I saying? If x approaches 5 from the negative side, then we can write x equals to 5 minus t. In fact, I'm gonna just simplify g of t right now because g of t looks really friendly. The 5s will cancel out, the negative signs will cancel out, and the t will become t over 6. It works. So fix epsilon bigger than 0, choose delta, so that when you stipulate this guy, t is positive, so g of t will be positive. To make this less than epsilon, we simply stipulate t to be smaller than 6 epsilon. That's it. Alright. Okay, we are making really good progress. And I'm gonna edit that question in a moment. So this one actually should be positive. Alright, let's do this. This is a negative infinity question, so once again, it goes to negative infinity when it's reciprocal, or rather when the negative of that goes to positive infinity, which means the reciprocal goes to 0 from the positive side. And since x goes to 4 from the positive side, we can replace that with t approaching 0 plus and replace x with 4 plus t. So let's do that. Fix epsilon bigger than 0, choose delta, restrict the inputs. We want the outputs to be, well, that. And this tells us, let's just do some algebra. Again, it's really the algebra that's doing all of the heavy lifting for us when it comes to finding these epsilon delta results. So we have that g of t would definitely be positive. Everything there is positive, so works out very nicely for us. So we get the 8 plus t term. We can control that if we let t be smaller than 1. Back to the usual tricks. We can do that. That is totally legitimate as far as I'm concerned. Whoops. So 8 plus 1. And finally, we can stipulate this to be smaller than epsilon via t being smaller than 2 epsilon over 3. That means we get that. Alright, we're on the home stretch. Let's go! Apparently, examples 95 and 96 are the same. So let's just kill 2 birds with 1 stone, because why not? Right, this guy. This is a legit question. Okay, I was a bit worried there. I thought the question was ill posed. Okay, this is a legit idea. Okay, yes, right. Okay, let's do this. So once again, this can be written as let's do it this way. since we are going to negative infinity, the negative of this guy has to be, what am I saying? Okay, let me just do it here. Since this expression is going to negative infinity, when we negate it, when we put a negative sign, it should go to positive infinity. And when we take reciprocals, it should go to 0 from the positive side. This is our, well, this is not our g of t, but more precisely, since x goes to 4 from the negative side, we can replace x with 4 minus t. And we can even do some simplification here, because we can do a bit of algebra right away to see that this guy has to be 2 minus root x as a whole, because you flip it, it becomes 2 minus x, and then you do a double flip, you get 2 minus root x. T 2 minus t from the positive side. Okay, so let's go ahead and prove this. Fix epsilon bigger than 0, choose delta, stipulate the inputs, and we are all systems go. So let's do this. Let's do some algebra. We definitely know that gt is positive because 2 minus t has to be smaller than t, but we need to make sure that we don't get any negative problems. So let's just make sure that 2 minus t is positive, which means that t has to be smaller than 2. We're gonna need at least this stipulation here, right? In the middle, at the very, very least. But even then, it's sort of, well, what do we do with g of t? We definitely know it's positive. So let's just rationalize the denominator and see what we get. I made a typo error. It should be replacing with 4 minus t. Apologies here. Right? I made a typo error over there. 2 minus root x, so replace x with 4 minus t. There we go. Okay, so all of these guys will become 4s. Don't think it affects too many things, so it's not the end of the world. This will simplify to t over 2 plus root of 4 minus t. So we've already established that we want to make sure that the expression, oh, this is not t being smaller than 2 anymore. This actually should be 4. We've already established that if t is smaller than 4, then we won't have to worry about the square root being undefined. So therefore, this whole expression, the denominator is lower bounded by 2. And therefore, the 1 over is upper bounded by half. In fact, g of t will be positive in this case. Right? And let's just do the grunt work over here. This will definitely be bigger than 0. So if we take 2 on both sides, we definitely get bigger than 2. We take 1 over. It's definitely smaller than a half. So we can bound this by t times a half. And finally, we can bound by epsilon because t will be smaller than 2 epsilon. So we stipulate these two requirements. And that is our answer. 2 in 1. Great. Not complaining. Okay. 97. When I look at the cube, it should go to negative infinity as x approaches negative infinity. Typo error there. So there are a bunch of, yeah, that's a typo error. It should be negative infinity. So this question is interesting because you actually see 2 levels of convergence here. The first level is that since x cubed is supposed to approach negative infinity, it's the negative of that. The negative of that should approach positive infinity, and then 1 over that should approach 0. Secondly, since we're taking x approaching negative infinity, we can make the substitution x equals to 1 over t. I mean x equals to minus 1 over t because of the negative symbol. And let's just do a little bit of algebra here because I think we can sort of see what's going to happen. This is going to be 1 over minus 1 over t cubed. The two minuses will cancel into 1 over 1 overs. Will give us t cubed. So actually, we're getting this simple expression. Let's just do it for completeness. I'm not even going to write gt this time around because it's pretty straightforward. This is t cubed, and to make it less than epsilon, we need to make this guy less than the cube root of epsilon. We're done. I'm not even going to write a gt this time around because it's pretty straightforward. Okay, we are almost done. We're almost done. We are at question 98. Whoo! All right, let's do this. Let's not celebrate yet. Let's just quickly get this over and done with. So, question 98. Let's do it. Let's do it. Let's do it. Let's do it. Okay, so we have this expression, and this expression is going to be an infinite limit again. And once again, this can be written as the negative of this expression going to positive infinity. Therefore, it's reciprocal going to 0 from the positive side. And since x is approaching positive infinity, we're going to replace t, or rather we're going to replace x with 1 over t. So this is our g, and we need to do a bit of algebra this time around. I am looking forward to finishing this. I am really looking forward to let's get a bit more space for the algebra. Right, so g of t is gonna be this guy. So let's do some calculations here. I believe this is gonna be I think there's a T8 on top. Yeah, there's a T8 on the top. Yeah. Okay, so this will simplify to, well. And this is why my friends do not celebrate so quickly, because now we have an irritating beast that is sort of stopping us from victory. Now, what am I going to do here? Well, this is, I'm gonna pull up a secret weapon, okay? So what I'm gonna do here is, I know that this guy is gonna give me some trouble. Okay, I know we could solve and all of that, but I know that it's gonna give me trouble. So I'm going to limit the trouble it gives me, right? I'm going to insist that the maximum error that this can produce is 1. And similarly, the maximum error that this guy can produce is 1. Why do I insist on that? So that when we take the negatives and then we combine the denominators, we will definitely get a positive number. So I'm going to cheat. This is a legitimate cheat. We didn't even solve anything, we just did bounding. We just insisted that those two things happen. we will be good to go. But let's quickly make the calculations here. So this will be t being less than the 4th root of 1 over 8. And this is going to be t being less than the 8th root of 1 over 48. Okay, we are going to stipulate these two requirements on t so that we can definitely deal with the denominator. So once that's the case, everything in the denominator is positive, everything in the numerator is positive, we are good to go. And the fraction is bounded above by half. So finally, we can bound it by epsilon by allowing t8 to be smaller than 2 epsilon, aka t to be smaller than the 8th root of 2 epsilon. We need these 3 stipulations. Rather complicated in the expression, but doable. And there we have it. That's it. So we can still do it using epsilon deltas. We can still use epsilon deltas for this. Okay, we are on our second last question. And I'm not looking forward to it, but I think we can do it. Woo! Oh boy. Feels like the final boss, you know. I should probably put some Rush E music here, but I can't. Okay, let's go! Let's go! Okay, now, once again, it's approaching negative infinity, and that tells us that that the reciprocal, the negative of this expression goes to positive infinity, which means that the reciprocal goes to 0 from the positive side. And we can also rewrite everything since x is approaching... Oh, x is approaching 0! So we can replace x with t. I'm gonna do the t just because it's a bit easier to handle t. My brain is so used to doing t, let's just use t. We're gonna show this result. Here's our g of t. Oops. This time, t is two-sided, so it's 0 less than modulus of t less than delta. What we need to show is that this happens. So that's algebra. And now the denominator is slightly troublesome because 1 minus t squared is equal to 0 precisely when t is equal to 1. So we actually need to, well, here's t and here's 0 and here's, well, plus or minus 1. So we actually need to choose something inside, and this time both sides kind of matter. So we will stipulate mod of t less than half, and I'm very sure this will work. So t squared will be smaller than a quarter, negative t squared will be bigger than negative a quarter, 1 minus t squared will be bigger than 3/4, 1 over 1 minus t squared will be upper bounded by 4 over 3, and it will be positive. So the entire expression for gt, okay, we have to be careful because now we actually need two-sided, so we can't really use the same arguments. So g of t is gonna be t squared is definitely positive. Mod of t plus 2 is mod of t plus 2, we don't know anything, times 1 over 1 minus t squared. So we know that the 1 over 1 minus t squared can be upper bounded by 4/3. And how do we deal with the modulus of a sum once again? We've not seen this in ages, but it goes back to the triangle inequality. Yeah, welcome back. It's been a while. So that's the triangle inequality once again. And we can now stipulate mod of t to be smaller than 1. So we already made one stipulation here, and here's a second stipulation. So we get 4 of mod t squared. This can be bounded above by epsilon when we stipulate that mod t is lesser than epsilon over 2. So with these 3 stipulations, and I do understand that the half and the 1, technically you can just choose half. If it's smaller than half, it's smaller than 1. Fair enough. This is more of, I'm not really thinking, so it works. It's still correct, so fair enough. And the grand finale! Alright, let's go! Here we go. This is the last question of the epsilon-delta marathon. And I think it's pretty obvious for everyone actually, because if you do some long division, you'll get it. But let's just go through the same arguments and call it a day. So, once again, since the expression approaches negative infinity, the negative of the expression approaches positive infinity, and then the reciprocal approaches 0 from the positive side. In fact, I'm gonna quickly simplify the expression this way. And we can write this as t approaching 0 from the positive side. In this case, it's x is approaching 0 from the positive side, so we can just replace x with t. I like to use t again because sort of we've been using t all our lives, so why not let's just end it off well with a t. So maybe let's just do some algebra on the g of t first. We actually get t to the 4th over 1 over 3 minus 2t4. Okay, so we'll come back to that in a moment. For the last time, fix epsilon bigger than 0, choose delta, then when t lies inside this region, we're going to show that g of t is positive and smaller than epsilon. Once again, we need to make sure that the denominator is positive, and once again, I'm going to cheat. I'm going to cheat because I'm going to insist that the maximum worsening of the expression, in a sense, is, you know, okay, so the minus 2t to the 4th is going to cause some loss, right? I'm going to limit the loss. So we're going to stipulate t smaller than 1. And the reason why is this, because t to the 4th, right, will be between 0 and 1. Minus 2t to the 4th will be between 0 and 2. This way, if I add 3 on both sides, the denominator will be lower bounded by 1. So g of t will still be positive. Alright! In fact, it will be bounded above by 1. Because you can take the 1 over. So finally, 0 is less than g of t is equal to t to the 4 over 1 over times 1 over 3 minus 2t to the 4th. We've seen under this stipulation that this fraction is bounded above by 1. And we can bound t to the 4th via the 4th root of epsilon. So finally, for the last time, that is our choice of delta, and we are done. Woo! 100 epsilon delta questions in 6 hours and 47 minutes. If you want to check out my calculus paper, click on the video on the screen that will appear somewhere, somehow.